Yeah, good. All right. Go ahead.
Welcome. I am Torsten Becker. I'm the chair of the Committee on Solid Earth Geophysics and member of the Board of Earth Sciences and Resources at National Academy of Sciences. It is my pleasure to introduce our spring meeting on glacial isostatic adjustment within a heterogeneous and evolving Earth system. Welcome to everybody here in the room and everybody online participating in what proves to be an exciting meeting. The National Academies are the nation's preeminent source of expert evidence-based and objective advice on science, engineering, and health matters. The goal is to inform policy with evidence, spark progress and innovation, and confront the challenging issues for the benefit of society. Among the activities are to serve as a neutral convening body to provide guidance on program direction and priorities, help resolve scientific or policy controversies, provide technical analysis and independent peer review, inform science policy debates, build and maintain scientific networks, which is what we're trying to help here, summarize state of the art in the sciences to audience of varying technical knowledge, and increase the visibility of emerging scientific fields and policy issues. Within the Academy of Sciences, our committee on solid earth geophysics has the goals of encouraging advances in our understanding and in the review and scientific exchange regarding topics that involve Earth structure, dynamics, and evolution. We seek to support community discussion and community agency interactions within the field of solid earth system science. We wish to foster long-term efforts to collect, store, and disseminate related data in an open and inclusive way, including for monitoring of geodynamical events and nuclear test ban treaty considerations. To do this, we conduct a range of activities, including meetings such as this one. We support reports and webinars, which can be accessed online. The committee is, in terms of its membership, it's listed here, and you will hear from some of my colleagues later in this meeting. Our sponsors are the Department of Energy, in terms of its Basic Energy Sciences and Geosciences Directorate, NASA, the Earth Surface and Interior Division, the National Science Foundation, particularly Division of Earth Sciences, and the Earthquake Hazards Program of the United States Geological Survey. And we thank our sponsors for supporting these efforts. You can find out more about our committee by following the link that is indicated here or taking a picture of the QR code you see on the right. We have an email list that we very much encourage you to join, and you can see a list here of past topics that illustrate some of the things that we are excited about in terms of facilitating the discourse in these emerging fields, established fields, and we are very much trying to support the interactions between science and society within the context of the solid Earth system. With this brief introduction, I would like to hand it over to my colleague at the committee, Jeff Freimüller, who will introduce today's workshop. And I would like to thank everybody again for joining for this exciting meeting. Jeff.
Thanks, Torsten. I'm Jeff Freimüller from Michigan State University. And again, our title today is Glacial Isostatic Adjustment within a Heterogeneous and Evolving Earth System. We have two panels. Sorry, got to get rid of a message on my screen. We have two panels today, two sessions. I'll be moderator for the first session, and Jessica Warren will be moderator for the second session. So each session has three speakers. In the first set, we have Rebecca Steffen from Lantmäteriet, Sweden, Lambert Caron from Caltech JPL, and Grace Neild from Durham University. And you can see the titles there on the screen. So without further ado, I'd like to turn it over to our first speaker, Rebecca Steffen. And her title is Comprehending Glacial Isostatic Adjustment Models. What are they and what do they tell us? And those of you online, you can join the discussion. There's a box for you to put in questions. We'll be taking questions for the speakers and moderating those questions as we go along. So with that, I'll turn it over to Rebecca, and if she could share her screen and begin the presentation.
Yes, thank you, Jeff. You're able to see my screen?
We see your screen, and we see everything is ready. So take it away.
Thank you. Yes, first of all, I hear my echo. I think you have to mute the room.
So we're not. Oh, sorry. I'll turn this off.
Good, perfect. Is it turned off? Yes, looks like. Good. Yes, first of all, I would like to thank the committee for organizing this meeting and for inviting me to speak here today. Before I will talk about what GAA models are and what they tell us, I would like to give a short recap of what GAA is. And GAA is the response of the Earth to ice mass changes, which means that when we build when an ice sheet is built up, first of all, we take water out of the ocean, which means sea level is falling in most places. And in the regions beneath the ice sheet, we have subsidence. And in the regions surrounding this ice sheet, in the peripheral bulge, we have uplifting shown by these arrows going upward. This process is instantaneous in the beginning because a lithosphere and a mantle are reacting elastically. If the loading is continuing for several 100,000 of years, the mantle starts to behave viscously, and then we have mantle flowing away from this subsidence region, and which means also that we have a kind of a time lag in this process. If the ice sheet is now melting, we put water back into the ocean, which means that sea level is rising in most regions, and we have now uplifting in the regions where we had the ice before, while the peripheral bulge is collapsing and we have a subsidence. Because the mantle is still responding viscously to this entire loading scenario, we still see this uplifting and entire GAA response even several 10,000 years after the ice is gone. But it's not only about the uplifting, subsidence, and sea level fall and rise that we see from GAA. GAA also ice loading induces stresses in the crust, which I will come back at a later point in my talk. And we also see a change in the location of the rotational axis when we increase or decrease the ice sheet. So now that we all know what GAA is, let's look at GAA models. So for a GAA model, we need input. One of the input is the ice model, as shown here. And this can be a paleo ice sheet history or recent ice mass changes. And once we use an ice load in a GAA model, we calculate also accompanying sea level changes because of the ice mass changes. And Glenn will talk about the ice model development in the last talk today. Another input is the Earth structure and rheology. And there we can have different parameters: mantle viscosity, lithospheric thickness, rheological parameters, and also different rheological models. And Harriet and Gigi will talk in the second part of the meeting today about these aspects. So now that we have two inputs, the ice loading and the Earth model, we have a GAA model. And then we can produce various outputs. So 3D solid Earth deformation, relative sea level change, rate change, and stress field rotation rate and strain rate. And the 3D solid Earth deformation then also has an influence on the ice sheet evolution. And if we have these outputs, we also can compare our model to observations and then adjust our Earth model and or our ice model as an input for the GAA model, and then rerun the G model again. We want to make this comparison to observations to better understand the GAA process, also to get constraints on Earth rheology that can be used in many other applications, and then also constraints on surface mass redistribution. So what is the purpose of the GAA model? We want to constrain regional Earth viscosity and ice sheet histories. We also want to, of course, tune the model parameters and then are able to provide a calibrated model that can be used in a variety of applications for the end user. What are these applications? Applications of a GAA model are basically almost endless. There are so many things that can be used where GAA model can be used. For example, to estimate hydrological changes from satellite gravity data, but also estimating stress changes to find stable locations for nuclear waste storage or obtaining sea level projections. Before I talk a bit more about what we get from a GA model, a short history overview of 3D GA modeling. It basically all started in 1935 with Haskell when he estimated the mantle viscosities based on GA observations. And about 40 years later, Peltier provided or published the first linear maximum model results. Maximum model is still one of the rheological models in GA that is commonly used, but meanwhile, different models are also applicable. Only 2 years later, Farrell and Clark presented the sea level equation, which is necessary to get the accompanying sea level changes from the ice mass changes and the response of the solid Earth. And at the same time, the GA term was defined. And in the early 90s, Patrick Wu was the first one then to present the 3D GA model. And since then, there are many other groups developing codes that are also capable of producing 3D GA model results. So let's look at observations. GA can be seen in many fields. For example, using geodetic observations, using GNSS data. We see here, this is an example for Northern Europe. The color scale shows the vertical velocity with a brownish reddish color showing uplift and the light green color showing subsidence, which we see in Northern Central Europe. While in the Fennoscandia, we see an uplifting signal with up to 10 millimeters per year. And the arrows show us the GNSS horizontal velocities, which are going away from this uplifting region. We can also see an uplift in Canada, shown by these red dots. And the blue dots show subsidence in the peripheral bulge, which is interestingly closely related to the Canadian-US border. But we not only see this uplifting and subsidence in regions that have been glaciated during the last glacial cycle, but also those in regions where we still have an ice sheet, for example, Greenland. And this also shows the vertical uplift, the pure GAA uplift, most likely. So elastic uplift is reduced, which is based on recent ice mass changes. And this leaves us with an mostly uplifting signal for the Greenlandic coast and a small region of subsidence closer to Canada. We can also use the technique of INSA to look at the vertical velocities. And this is an example from 2004 from Amandine Aurillac, where she looked at the response of the solid Earth to glacier mass changes. And we see also up to 12 millimeters per year of uplift. And then we can also use geological data that show us something about the 3D land motion and also vertical land motion using lake levels in Canada to over time to estimate where was the lake level and showing us a tilting. Now, how does this compare to model output? And this is now a result from a recent code development, a 3D GA code called FEM-IBSF, which is based on the paper by Pingping Huang. And here we use I6G ice history together with a 1D VM5A viscosity structure. But the code is capable of using also 3D structures. And what we see is now the vertical velocity. And this is quite similar to what we observe also with GNSS data. We have uplifting in North America and Northern Europe. And in Greenland, it's kind of a mixed area, right? Same for Antarctica with mainly uplifting. But you see that the vertical velocity is not zero even for the entire world. We have even in other regions that are further away from the ice sheet that are responding to ice mass changes because of the change in the ocean load. And Grace Need will talk more about the GNSS aspect of GA in her talk. Another geodetic application where we can observe GAA is gravity changes. Looking at the satellite data first, this is a trend from the Grace satellite data set. The geoid height change, which is quite similar, giving us a quite similar result to what the uplifting we have seen before. We have an geoid uplift in the North American region and also Northern Europe. And of course, we see something else in Greenland and Antarctica because we have the melting ice sheet. So Grace shows us GAA and many other processes that are ongoing. We can also observe gravity changes by ground observations. This is for a station in Finland, where absolute gravity measurements have been taken for several years at the same location, and then we can make a nice show a nice decrease in the gravity value. And this has been done for many locations in Northern Europe, and this is now the result of it. Looking at entire Northern Europe, we see a negative gravity change, because the land is uplifting, so the points are coming further away from the Earth's center, and so gravity is decreasing. So how does it compare now to the model output? Using the same model code as before, looking at the geoid change, and this is quite similar to what we see from GRACE. We see this uplifting region in North America and Northern Europe, and such a model could be now taken as a reduction model for GRACE to remove the GA component in GRACE data. And Lambert will talk about this in the next talk in more detail. Another geodetic observation is Earth rotation changes. And here we can, for example, look at polar motion, which means that the change in the location of the Earth rotation axis, as shown here, from 1900 to 2000. We can also look at the change in the length of the day and compare this now to the model output again. Now we plot also a polar plot. We calculate the modeled polar motion change and compare it to the observations shown by the green cross and the orange star showing the modeled output. Of course, there is a mismatch, because it's not only GA that leads to polar motion. A more geological observation of GA is relative sea level, and there we can go back many years, several tens of thousand years back in time, and these data are also usually used to estimate or validate the ice model that are used for GA modeling. Then we can go to more recent time. We can look at tide gauge stations. This is a result from the tide gauge curve from Stockholm, where sea level is falling because Stockholm is in Sweden, and so it's uplifting the region. And then we have more recent data from altimetry, satellite altimetry, also telling us something about sea level change. And how does it compare to a model output? And here we can plot the relative sea level rate. And we see, of course, in regions where we had the ice, the land is uplifting. So, of course, sea level is falling in that case. And another observation of GAA, which is not so often used, is seismicity. What does it mean? So, for example, in Northern Europe, we have evidence that earthquakes happened at the end of the deglaciation, or even during ice advance. And how does this evidence look like? So, for example, for northern Sweden, we have the more famous fault, the Prairie Fault, and you can see a fault trace of this fault. And if you go to one of these locations on the ground, you can see a sharp increase in the landscape, which clearly says that there was an earthquake after the ice was gone. And this is also visible, or GA-induced seismicity is also visible in Central Europe, but there we don't see such a clear offset in the landscape, but we have soft sediment deformation structures, which tell us that an earthquake happened quite recently. And how then can we compare this to observation, to modeled output again? Now looking at the column failure stress changes, to introduce the column failure stress. The column failure stress is the distance between the Morse circle, which is defined by the principal stresses, and the line of failure, and easily saying if this delta CFS is smaller than 0, which means that there is a distance between the circle and this line, then it's stable, which means the blue color in the plot down here. If the circle crosses this line, delta CFS is positive and it's unstable. We can have earthquakes. And what we see for the delta CFS for today is that we have unstable regions in almost entire Northern America and also in parts of Northern Europe, and also for Antarctica. And you see that, again, like with the vertical velocities, even in regions that haven't been affected by an ice sheet, we see a change in the column failure stress because we have ocean load changes as well, and GA is a global process. I will focus now in the rest of my talk on this seismicity, because we don't have only for Northern Europe these traces of glacially triggered earthquakes. We also see these in North America, Greenland, and even Antarctica. And to give you a bit more background why we get these stress changes, why do we get earthquakes because of GAA. So when we have a load, we induce stresses. One stresses are in the vertical direction. These are only the loading stresses and only exist beneath the ice sheet, which means that if the ice sheet is gone, these stresses are also gone. In addition to the loading stresses, we have flexural stresses in the lithosphere because the flexure as a lithosphere is bending because of the loading. And these are acting in the horizontal direction. We have compression in the regions beneath the ice sheet, while we have extension as soon as we get out of the ice sheet and ice margin towards the peripheral bulge. And then we have an additional stress component which comes from the migration of stresses from the mantle into the lithosphere, which I will explain now. So in the beginning of the loading, as I mentioned earlier, we have an instantaneous elastic response of the lithosphere and mantle, and those stresses are built up in both layers. If when time of loading is continuing, like it was for the last glacial cycle, the mantle starts to behave viscously, and then the stresses are transferred towards the elastic layer. And with continued loading, the mantle is completely reacting viscously, and the only elastic layer left is a lithosphere. And as a viscous layer cannot hold the stresses in the same way as an elastic layer, the stresses from the mantle are migrating, that were created in the beginning, are migrated towards the lithosphere. Which means that if we model glacially induced stresses, we cannot just use a lithosphere model, because then we miss this important aspect of stress migration next to many other aspects of GA modeling. But so it's important when we model GA stresses to use a lithosphere and a mantle model. In addition, stress migration means that if we take just the vertical or the velocity field from today or any other time in the past and convert it to a strain field, and also then convert the strain field to a stress field, this can be done by mathematical equations, we also miss the stress migration because this is then not included. Which means that when we want to model GAA stresses, we have to use an entire GAA model together with an ice loading history to get all three stress components. Now showing glacially induced stresses for two examples. The first one is for Greenland. Again, blue is stable, red is unstable, and you can focus on the bottom here. It goes from around 14,000 years until today. And you see how this southern region of Greenland is becoming unstable. Let's look at this location down here. And looking now at the data CFS over time from 20,000 years before present to today. And here is the ice load shown. We see an increase in the change in column failure stress around 10,500 years ago, which means that there is a likelihood for an earthquake. And in this publication that was published about 4 years ago, we also present evidence that we might have had an earthquake there. Another example is glacially induced stresses in Arctic Canada. Again, we look at this column failure stress now shown on the right side. The left side shows the ice model history. Again, blue is stable, red is unstable. And just to give you a short overview where we are. So this is Baffin Island. Over here is Greenland, Ellesmere Island. And here we have Somerset Island and Prince of Wales Island. And Hudson Bay is basically down here. Running this now again from during the last glacial maximum to today, we see stable regions, but as soon as ice is gone, the region becomes unstable with quite large values of up to 6 megapascals. Again, looking at one specific location between Somerset Island and Prince of Wales Island, we know also the Earth model, so showing the results of different Earth models. And what is quite interesting is that no matter what Earth model we use, the activation or the time when delta CFS becomes positive is the same. This is not the same for the ice model. There we can have a large variety of change in delta CFS, and this can be between 12 to up to 5,000 years before present for this location. So it's more important to know the ice model when we look at stresses than looking at the Earth model. At the end, I want to also mention about GAA model uncertainty, because a GAA model is still just a computer model, which means that we have uncertainties that come from the model input parameters. This diagram from Pippa Whitehouse summarizes this nicely, because if you look at a large ice loss at 10,000 years versus a small ice loss at 5,000 years, we still see the same observed present-day uplift rate that we can see from GNSS data, similar for this other example down here. So it's important to also use several observations when we compare our model output, not just only one observation. Another aspect is that we might miss model physics or have simplifications in the model setup that introduces some uncertainty. If we use, for example, a compressible model, which is more realistically, versus an incompressible model, easier to calculate, but this can give us differences in the horizontal velocities as shown here, and these differences are larger than GNSS uncertainties have to be considered. So it's better to use a compressible model when looking at horizontal velocities and even other GAA model outputs. And with this, I would like to sum up already, and thank you for your attention. And I hope you have learned something and have some questions. Thank you.
Okay, I actually have one question while we wait to see if we have some from the audience. You showed that for the continental ice sheets, that knowing the ice model was much more important for understanding the stresses than the Earth model itself. Is that also true when we look at, let's say, smaller ice masses in present day change? Is it mostly uncertainty or the ice model uncertainty, or does the Earth model uncertainty become more important in that case?
Honestly, we don't know. But I would say the ice model is the most important constraint that we have. We have to know the ice model better for the stress changes, and then we can look also if the Earth model changes tell us more.
We have one more question in the room here.
Yeah, thanks. I was wondering, given the uncertainties about the background stress levels and amplitudes of triggering stresses, if you've looked at the style of the stress change as might be reflected in geological records of changes in how faults are loaded, or as for the present day in terms of the focal mechanisms, to see if you can divvy out where you're actually seeing those stress changes due to GI.
We see these stress changes. No, I'm echoing again. Yeah, we see the stress changes when we look at these previous faults. If you look at Antarctica, we can also look at the more recent earthquakes, of course, but this hasn't been touched yet so far, because also the Antarctic ice model is not good enough at the moment to look at these, because we know we need to have good ice model. And then the background stresses is an issue in our stress estimates, definitely. And we always assume that we have a critically stressed crust, which is a kind of valid assumption according to the seismologists.
Okay, thanks. Thanks, Rebecca. We'll need to move on to our second speaker, Lambert Caron. We may have time for more questions at the end of the first panel. So, Lambert, are you ready?
Yeah.
Okay, all right.
Well, I'm just waiting for my slide. Okay, good. I hope you can hear me all right. Yes, I need to just look in the same direction. Okay, so yeah, thank you for inviting me today. So I want to touch on two main topics today. One is explaining a little bit what GIA uncertainties are limiting in terms of the interpretation of geodetic data. And the second part of my talk would be trying to understand where this uncertainty comes from and how it might change in the future when people revisit certain aspects of the modeling. Next slide, please. Okay, so for those of you who are unfamiliar with GRACE data, so it is a mission composed of a pair of satellites, and the main instrument on board is a radar that measures the distance between the two satellites. And the principle is when the first satellite goes over the point of the Earth where there's an excess of mass, it's going to accelerate due to that gravitational attraction. And then the distance between the two satellites will increase. And then the second satellite will catch up to the first one when it passes that same excess of mass and essentially resume the baseline distance. And then the opposite will happen if this pair of satellite goes above an area which is has a negative mass anomaly. And so in this way, we can image the distribution of mass over the solid Earth. And so there's really three different levels of products that the GRACE mission gives us access to. Level one has to do with the instrument. So it's going to be the ranging itself, as well as other properties like the satellite clock that's on board. And then the level two is the interpretation of that data in terms of gravity field. So we know we have a mathematical framework to translate that ranging into a set of gravitational attraction. But we have to make a few steps, a few corrections to get there, remove the non-gravitational acceleration when the pair of satellites is correcting for the right orbit. There's thrusters that are going to set the satellites back into the path when they have to move away from an obstacle. And then level three is what most users want, and it doesn't have to do with the gravity data in and of itself, but rather the interpretation of that data in terms of distribution of mass at the surface of the Earth. And in the biggest communities that use GRACE data, well, they want to know what the distribution of water mass is and not distribution of mass within the solid Earth. So we're going to talk about communities in the hydrology, physical oceanography, and then as well the people that study the cryosphere. But to get there, we need to remove from the gravity signal the part that is due to the solid Earth itself. And so within these corrections to go from level 2 to level 3 is remove GIA that I highlighted here. And then that's kind of the main point that we'll see today. Next slide, please. Okay, so I'll give you a few examples of what type of data we can see in GRACE. So this is a comparison between two different months. And what you see in color here is the mass anomaly at these two periods. So we had a really intense drought in Southern California a few years ago. And that's why you see these intense red colors. It was large drought, which means a negative mass anomaly. There was no water, so low mass. And then after a very rainy winter, we got that picture that was almost on average 0, even maybe a little bit blue. So we can see that in the GRACE data, the resolution is not very high, but the quality of the data is very clear. And if we look at the GIA correction from our model here, the uncorrected GRACE before removing GIA will be somewhere around 13 millimeter equivalent water height. And then once you correct it, you're going to remove 4 millimeters here, and you'll be left with about 9. And the error is about 2.5. So this is not too bad. This is not, if we get GIA wrong, we'll not misinterpret that data. The other thing I wanted to show here is that we're going to talk a lot about trends today, but there's also valuable information found at the interannual and seasonal timescales. Next slide, please. One of the main applications and the clearest signal you'll see in GRACE is the changes in the ice sheets. There's a very, very strong signal coming from there, especially it's very consistent across time. So these are the time series that I extracted from the integration of mass over the entire areas of Greenland and Antarctica. And so we're talking about several hundreds of gigatons per year of mass loss. And the GIA correction for this area, it's pretty small for Greenland, although there's a big uncertainty on my part here. But over Antarctica, there's a roughly the same order of magnitude between the GIA correction and GRACE before the GIA correction. So you're nearly double the estimate once you do the GIA correction. So there, having the right model matters more. And there's some disagreement, although the field is starting to get better at this over this region. Next slide, please. And then the final let's say, community that uses GIA is the community of physical oceanography, and there's a particular interest in the Northern Atlantic because we tentatively see a low mass trend in the North Atlantic, and that could correlate with a weakening of the ocean circulation, which could have really big consequences for the climate. So we need to know whether that's true or not. And as we'll see, it's really difficult to interpret. Next slide, please. So I put here together the 20 years times trend from GRACE that's corrected from GIA already at the top left. And then at the bottom left is my estimation of what the mean GIA correction is. And then you'll see to the right of that, the GIA uncertainty. Now, the interesting part is how do you compare the corrected GRACE with the GIA uncertainty? If you do the ratio between the two, that's A divided by D here, then you'll get an idea of the areas where the GIA uncertainty limits the interpretation of the trends, right? So if you're in the region where the GRACE signal is between 0 and 1 sigma of GIA, there's not much you can conclude from the trends. Could go either way because it's smaller than the GIA uncertainty. If you're between 1 and 2 sigmas, you can tentatively interpret, but with a lot of caution, because there's a lot of chance that, you know, an error on the GIA could compromise what you're concluding here. If you're between 2 and 3, you can make a good case for the trend being reliable. And then if you're above 3, yes, it matters that you do remove GIA, but you're not going to be wrong if you pick the wrong model. Okay, so that's what I wanted to show with that map. Can we move on to the next slide? Oh, that's the previous one. Thank you. Yeah, so this is just the blow up of that map from before. And then you can see a few areas which are important. Over North America, you're in that 0 to 1 sigma order of magnitude. And that means it's really difficult to interpret the hydrology changes, at least in the trends, over that region. There's also, we talked about the Northern Atlantic and whether or not weakening of the ocean circulation was happening. Well, that's also in the area because it's so close to the Laurentide where we can't really conclude what the trend is doing. There's too much uncertainty. And then the last point I wanted to show is East Antarctica, even though this is showing that you can have reasonable confidence if you look at now, not just my model ensemble, but also what other people in the community have modeled, then it gets really difficult to interpret what's going on because we have a poor understanding of the ice history in that region. Next slide, please. Okay, and that's sort of what you can see here. This is from IMBY, and they had different methods to interpret the mass change in Antarctica from different parts. And what you can see here is that the total mass trend over Antarctica, that's the purple line, is pretty well aligned and dominated by West Antarctica. But the uncertainty mostly looks like the uncertainty that you have on East Antarctica, and that's because of GIA. Because we, again, know little about the uncertainty over there. Next slide, please. Okay, so if you make a huge big picture of how we construct these forward models and uncertainty estimates, these are to me, these are the big categories of inputs you need to consider and frameworks. So as Rebecca said, on one part, we have ice history, we have rheology, and both of these contain differences between estimates and uncertainties. You'll put together that into a particular model, and then that's where we may have these disagreements over the physics. We need to agree on what the constraining data is, and we don't. We don't all use the same data set. Then we need to agree how we use that in the cost function. Are we grouping the data? What are we doing when we mix in GPS with relative sea level data, for example? And then out of all these ingredients, then we have an uncertainty estimates. Next slide, please. So these are all the questions I ask myself when I put together a joint model where I'm going to interpret some kind of uncertainty quantification from a model ensemble. Next slide, please. Okay, so there are some considerations to have as to why this uncertainty exists. So it's not just that the inputs are not known perfectly. There are some specific problems that cause the result to have significant uncertainty. One is that we don't have even data distribution. So this is the common case among other geophysical fields, but I wanted to show you here the distribution that we're dealing with. So this is a combination of relative sea level data, and in red here are the GPS sites that I used in this 2018 paper. So you see they're mostly concentrated around the last areas of the glaciation, makes sense. And then sparsely, I would say in the far field, we have some coral data and other such data. So big spatial gaps. Can we move on to the next slide? If you look at it in time, that's the graph on the right. This is data distribution again versus time and then longitude. So you can match it with the map. And here what you see is that we have mostly information over the last 10,000 years and then fewer amount of data before 10,000 years ago. And that's where most of the active deglaciation happened. So it's difficult to deal with it because we're sort of biased towards the recent. Next slide, please. Okay. Additionally, this is an example of a particularly, I would say, bad site for relative sea level data. There are some problems that we can see in the data, some limitations that explain why we can fit several models with different inputs in there. One is that the quality of the data is not necessarily sufficient to rule out a lot of parameter combinations. So you can see here, especially on the latter part, there are some gaps in the data. There's sometimes biases because the geological data can be reworked, or there's some problem with the datation. And there's also missing data from the early phase of the deglaciation. So this all means that several curves could fit in that time series. Next slide, please. Nonetheless, I would say this is one of still the only source of time-dependent data. And as Rebecca showed, this have what we have to work with right now. So how are we going to derive uncertainty estimates at all from here? So I show you here now my approach to it. So I take the simplest model I can do. So a 3 layers mantle with upper mantle, lower mantle, and lithosphere. And I'm going to vary the viscosity structure in there. And then I'm also trying to quantify the uncertainty that stems from the ice history. We don't really have good ways to do that right now because ice models are expensive to run. And so my approach has been, let's try to at least rescale the ice history by region. We'll take ice5G or we'll take the model from the ANU. And then say we'll try to modify that, put 10% more ice in Antarctica, and then lower a little bit the ice volume in Fennoscandia and see what happens. So this way you can have some big picture idea of the uncertainty from the ice history. So you put that together, and then you can generate just a bounty of forward models because they're cheap to run in this way. And then this is an example of these model ensemble on the right, where you have several curves of GIA model, and then in black are the data. And you can see we can attribute certain weights based on the model performance here. And then from this set of forward curves, we can derive GIA statistics. That's how we do it. And then I put the formula for the probability here. So it's a probabilistic approach to uncertainty. Next slide, please. Okay, so if you get the result of that, the nice thing is you don't really have to assume much else in terms of error structure. And what you get is a probabilistic representation of the parameter you put in there. So these are the marginal probability distributions for the lithospheric thickness, upper mantle, and lower mantle viscosities. And you can see they have some interesting properties. They don't look like Gaussian structures. They are asymmetric. They might be multimodal, and yeah, there's not really a formula that you can easily fit to these curves, but they are very interesting nonetheless. Could we move on to the next one? Yes. So one thing to consider if you look at that is that most people will try to optimize their model parameters to find the best fit. If you do that here, you obtain the black cross. And so what's interesting to see here is that this is very different from sort of the average model that you would get from this, even if you weigh it by the probability. And it's not so far away from the estimate that you get from IS5G VM5A, for example, or IS6G. So big difference between average model and best fit models because of that asymmetry. Next slide, please. And if you do that in 2D now, so you're looking at the probability map versus two parameters at the same time, then you can start to see the correlation between these parameters. And again, what you see here, it's multimodal, and the correlation is not linear. So you have this interesting saturation effect. After a certain amount of viscosity, you don't change the relaxation curve because there's no viscosity active at all. Yeah, so this is an interesting property of Monte Carlo type of model explorations. And you're trading the simplicity of the physical model for the complexity of the error structure that you can get in this way. Next slide, please. So this was for Maxwell rheology, so very traditional. And I did try in my PhD to switch that to Berger's rheology. So it's a model that features a transient relaxation as in addition to the steady state. And what you see is that you do get something that's similar, but now the probability is shifted and that multimodality is toned down. So interestingly, we can measure random uncertainty very well with MCMC, but we need to remember that we also have structural uncertainty that is baked in the assumptions of the models that we use. So for example, the type of rheology, but also whether or not you use a ice history model that is physical or just empirical. Next slide, please. All right, so I just take the case of rheology here to make that point. So on one side, you can have the simplest 1D Maxwell model, not many layers that you can have. The advantage is that it's cheap, and you can probably compute a forward model in minutes. It depends on your exact technology. It is affected by more biases because it's less realistic. It doesn't have all these fancy physics that we know are probably true. But it makes non-uniqueness easy to explore. Now, on the other side, you have everything that we are trying to do today. So transient rheology, 3D structures, maybe a fine radial structure that matches more the tomography models that we have. And this is hard to quantify if you look at it from an uncertainty perspective, because it has many degrees of freedom. Next slide, please. And so there is a tendency to have to move towards more physical complexity in the models, which we very much need because we need to reduce the biases that's in our models. But oftentimes that will mean we need to think about how to not lose the information that we're getting from the error structure. And so we sort of have a gradient here of different methods we can use to explore ice history, model uncertainty. So on one side, you could have methods that allow you to get arbitrary distribution functions like Monte Carlo method. And then in the middle, you get something where the error is linearized, but you can still look at it. So that would be method like least squares or geojoint. And then maybe the simplest you can get is just compute a handful of forward model and you'll get an order of magnitude of the error. And then all the way at the end, you have, I didn't do the uncertainty over that parameter. And then the important thing to remember is that you might have a different scheme for each of the boxes that I highlighted before. So one scheme for the rheology and a different one from the ice history. And then maybe you won't look at other inputs of the model at all. So it's a mix, and we'll sort of do that. Next slide, please. So we're looking, several groups are looking into emulators to fix that problem, make a model that's both realistic and cheap. You do need to train the model, but that's a possible avenue that we're only starting to now really exploit, I would say. Next slide, please. Yeah, so I get to my take-home messages here. So again, the first thing we saw is that there are regions of the globe where geodetic data is complicated to interpret because GIA is in the way. and the uncertainty of GA is too big compared to the signal. There's mostly two categories for that uncertainty to come from. There's biases, structural uncertainty, and then there's parametric uncertainty or random variables. And then I would say ultimately that the uncertainty comes from the fact that our constraining data is imperfect and leaves room for all these different models to have either a similar prediction or just a different prediction, but not big enough that it's going to exceed the model uncertainty. And then there's a trade-off between the model, the complexity, physical complexity, and the complexity of the error structure that we get. That's it for me. Thank you.
Thanks, Lambert. One quick question. I think, historically, the ice models were usually optimized along with the Earth models, with the rheology models, which creates a trade-off essentially between ice history and rheology just from the optimization itself. How close are we to having ice models that are not really tied to a particular rheological model that you could fully sort of treat them as independent variables?
We're not close to that. I don't think we will ever be able to do that, actually, unless maybe somehow we get so much geological data that we can have constraints that are independent of the deformation itself. We're not going to be able to do that. Our knowledge of the past ice history is tied to these relative sea level curves, and there's no way we can't do both at the same time. I think what will happen is that we'll get better at inverting them jointly.
One more question here. Actually, two more questions from the committee, and then we'll move on to the third speaker. And for those of you who are online, if you have questions for the speakers, start queuing them up. We'll have a Q&A period after the third talk. So Torsten and then Steve.
So it seemed like you were able to reduce the bimodality in those trade-off plots by introducing the transient Berger rheology, but that transients, if I saw correctly, would then apply for the lower mantle. And so I was wondering if you think that's true transient behavior, or maybe that's actually spatially mismapped 3D variations in viscosity.
So from the pure cost function, you might be able to get away with doing a different refining of the mantle and mostly solve it. But from a theoretical point of view, and I think Harriet will talk about that, there's not really any reason to dismiss all the evidence that we have that there's going to be multiple relaxation time for the same material, and that's true for all depth of the mantle. So the lower mantle and the upper mantle most definitely have a component that is transient. And we just need to be able to see how we can constrain that within the resolving power of the data.
So you did a good job at telling us how complex the problem is, but I'm wondering, say if the community wanted to make a big advance in GA amount in the next decade, say, what are I don't know if there's any low-hanging fruit, but where should we put our efforts in terms of GA research?
So we're already well engaged to tackle the existing biases in the model space. I think the community is doing a really good job of doing that. Something else that the community is working on, but maybe gets less visibility, is more standardization of the way we constrain the model. So what compilation of data we all use for now is still very different. There are some efforts to standardize that. For example, whole C. They're doing a common database, which means all the data will be treated the same. And hopefully more of the community will rely on the same data sets to arrive to the same problem. And then the other part of that question is, how do we tie in these different data sets, the GPS, the gravimetry, the paleo sea level data, into one cost function? Because again, there's no standardization. So we all come up with different answers because we do the cooking a little bit differently.
Okay, thanks. We'll move on to the third talk in this group, which is from Grace Neild from Durham University. And Grace's title is Constraining Short and Long-Term GIA with GPS Time Series. And again, for those of you online, please go into the box and add your questions, and we'll have a Q&A period after Grace's talk.
Okay, great. Can you all hear me okay?
Yes, it's all good, Grace. Ready to go.
Perfect.
Go ahead, Grace. We're ready for you.
Yeah, sorry, I'm just trying to find my laser pointer. It's disappeared. There we go. Okay, so I'm going to talk about constraining GIA with GPS time series. And I'm coming at this from a modeling perspective. I'm not a sort of GPS data person, but I would really like to acknowledge all the people listed on the slide there, amongst many others who have put in a tremendous amount of effort to install these networks and to process the data so that modelers like me are able to use them. So what is GPS or GNSS? I kind of use these two terms interchangeably. That's not strictly accurate. GPS is a type of GNSS, but I'll stick with GPS just for this presentation. So there are stations all over the world recording very precisely the Earth's movement. So that's things like tectonics and seismic deformation, tidal motions, Earth rotation, and why we're all here today, glacial isostatic adjustment. This is an example of a GPS site in Antarctica, and you can see the monument there that's bolted into the bedrock, and then we have the GPS aerial in the radome sat on top. There's also associated equipment with that as well to provide power and to transmit the data. So for many regions of the world, it's fairly straightforward to install these things, but for the regions where we want to measure GIA, such as Greenland and Antarctica, there are other considerations for installation. We need to have bedrock that has to be ice-free, and in some regions of Antarctica, that's quite tricky to find. We need to have power so that they can keep running through the long, dark winters, and they have to be accessible either by ship or by aeroplane. So how are GPS used to constrain GIA models? Well, Rebecca introduced this really nicely earlier on. The simplest way is just to compare our model predictions to the GPS observations. So we have our two inputs to our GIA model. We have the ice history and the Earth structure. They feed into the GIA model, and those predictions can be compared to observations. So with these three components of the system, actually, if we know two of them, we've got a really good chance of trying to figure out the third one. So, for example, if we know our ice history really well, and that does happen if we're looking at ice history over the past couple of decades rather than over thousands of years. So if we assume we know our ice history really well, and we've got our GPS observations, we can use these two aspects to constrain our Earth structure. So GPS can also be combined with satellite altimetry and gravity data to derive empirical estimates of GIA. I'm not going to talk any more about that in this talk. So having a look at the GPS networks, we've got the Greenland network, the GNet stations. These are really nicely distributed around the coast of Greenland, and that really helps to have that spatial distribution to constrain the GIA models. In Fennoscandia, Rebecca already showed a really nice plot from this network. There's a really dense network all across this region of Fennoscandia and the surrounding areas with which to constrain the GIA models, and that's because it's all ice-free. Down in Antarctica, there are several GPS networks in operation. In addition to the IGS sites, There's the PolNet sites, the UK ANET network, and the CADA GIA network. And in Antarctica, it's a real sort of international effort to kind of keep these stations going. And it really needs a kind of multidisciplinary approach. So many stations are actually co-located with seismometers, for example. So this figure here, courtesy of Terry Wilson, shows continuous measurements of bedrock vertical land motion from around Antarctica. And you can see actually a relatively dense network of stations across much of West Antarctica. Now you'll notice one very obvious thing from this plot, and that's these absolutely enormous uplift rates that we see from the Amundsen Sea sector of West Antarctica. And these rates are around 5 centimeters per year. And that is just a phenomenal amount of uplift that we wouldn't be able to see without these GPS stations. The other thing that you might have noticed is that there's a change from uplift to subsidence over relatively short spatial scales. So we're actually seeing subsidence really quite close to this area of huge uplift. And also in the Antarctic Peninsula, we see subsidence at these two sites here, which is, and they are around 100 kilometers from uplifting areas. So having this dense network really helps us to capture these kinds of changes. Unfortunately, there's an uncertain future for these GPS networks. The US ANET network, or the PolNet network, is due to be decommissioned next year. And if that happens, that has a pretty devastating impact. It leaves a massive amount of West Antarctica unmonitored. And particularly for the Amundsen Sea region, which is the region of rapid change, that loss is quite devastating, really. For the UK ANET network, so that covers much of the Antarctic Peninsula and a few sites over in Coatsland, that was also due to be decommissioned by next year, but I'm pleased to be able to say that we're going to keep around half of those stations within the network, and that's due to continued support from the British Antarctic Survey, and that there are other applications of this network. So moving on to East Antarctica now, we're focusing on this huge area of coastline all around the east. This figure, courtesy of Matt King, shows 5 different GIA model outputs for that section of East Antarctic coast. And you can immediately see absolutely huge differences between these models, both in terms of the magnitude and also the spatial pattern. So this really shows that GPS stations are needed here to constrain these model outputs. So this figure just shows the RMS between those models, along with the long-running sites in yellow, and also GPS stations that have been installed since 2016 in the pink triangles. There are more stations planned across this region, as shown in this figure with green dots, and that would really help massively to sort of fill in the gaps between these other stations and really help with constraining those GIA models. Okay, so what is in a GPS time series? Well, if you've never really looked at one before, it might look something like this. And this is raw GPS data from O'Higgins, which is in the Northern Antarctic Peninsula. So we have an east displacement, a north displacement, and a vertical displacement. And we might see things like outliers in the data time series, or gaps where the power might have gone off or the equipment might have stopped working for some reason. And all of this raw data needs processing. We might also see offsets from, for example, instrument changes. Like you can see in this example down here, the instrument was changed and it causes a large offset in the data. And these are the kinds of things that need correcting before people like me can use them for constraining models. And of course, there are many geophysical signals that are being recorded in there and climate processes. So I'm just going to illustrate why we want to keep these GPS time series and why it's important to have long continuous data. This is a vertical GPS time series from Palmer, which is in the Northern Peninsula here. You can see about 9 years worth of data here. And I think we'd all be quite happy to put a straight line through that and say, yeah, that's our GIA rate, and we can use that for constraining our models. However, that doesn't tell us the full picture. This station's actually been operational since 1998. And if we look at that full time series, we can see quite large deviations from that inferred rate at the beginning and at the end. And actually, in the past few years, this station looks like it's been subsiding. So this is one of the reasons why we really want to be able to keep these stations active and continue recording data. These longer time series give us more reliable rates. So one of the other signals that could be in the data, and it could be contaminating the data if you're trying to use it for GIA purposes, is post-seismic deformation. So you might not think that this is much of an issue in Antarctica, but actually it is. So this was first looked at by King and Santa Maria Gomez in 2016, and they looked at this earthquake that happened around 600 kilometers from the east coast of Antarctica. So this 1998 earthquake was really large. It was 8.2 magnitude. And luckily there was a GPS station active at this time. And these time series showed a large offset at the time of the earthquake, which corresponds to the co-seismic offset, and then subsequent post-seismic deformation, which is the viscoelastic relaxation of the lower crust and upper mantle due to that large stress change. Over in the Antarctic Peninsula, the same thing is happening. There was a large earthquake that happened in 2013, a magnitude 7.7. This happened around 700 kilometers from the tip of the peninsula where there's a GPS currently active. This is the O'Higgins GPS time series. There's a large co-seismic offset again at the time of that earthquake and subsequent post-seismic deformation. So not only is this an interesting signal to look at in its own right, but it could contaminate the GPS time series or the inferred rates if we're trying to use those to constrain our GIA models. So having a look at some long-term and short-term GIA now. So just to be clear what I'm talking about when I talk about long versus short term. So the long-term GIA is that's already been introduced really nicely by Rebecca. So this global response to deglaciation from the last glacial maximum. So we're talking about millennial timescale changes, this sort of long, slow response where we have high viscosity mantle of around 10 to the 21. When I talk about short-term viscoelastic deformation, this was focusing on the sort of bedrock deformation part of GIA rather than the sea level changes. This is more relevant for regions with low viscosity, and we're talking sort of 10 to the 18, so that's several orders of magnitude lower than the global average. And these regions are responding to ice loading changes on sort of years to decades to century timescales. So our long-term GIA, this is an example of the I6G model for North America. And you can see the background colour here is the model predicted uplift or subsidence rates. And the dots there show the GPS observed rates. And by comparing the model with the GPS observations, this can highlight regions where there's deficiencies in the model. Perhaps the ice loading model is not quite right, or points towards needing a different earth structure. So down in Antarctica, this is the W12 GIA model. The background of that figure there shows the model outputs, and the dots show the GPS observations. And these authors did the same thing. They compared the model predictions with observations. So anything that plots along that dashed line gets it absolutely perfect. And anything that plots away from that line shows deficiencies in the model. So the authors noticed that the model significantly overpredicts uplift rate in the Antarctic Peninsula. So they tried to adjust the model by adding ice loading in the last 2,000 years of the model run. try and get a better fit between the model and the observations which they did. Of course, subsequently, it's become apparent that this mismatch is due to deficiencies in the 1D Earth structure rather than the Earth model. So moving on to short term now, in the Northern Antarctic Peninsula. So the Larsen B ice shelf collapsed in 2002, and subsequently glaciers feeding the former ice shelf began to speed up and lose mass, and this was recorded in elevation change data. So luckily there's the Palmer GPS station, which is operational over here on the west of the peninsula, and this showed a really clear change in uplift rates in early 2002, which coincides with that ice shelf breakup. So it was hypothesized that this uplift was due to a purely elastic response of the solid Earth due to that ice mass loss. But when we did the modeling for that, even within the uncertainty bounds of the ice mass change data, we didn't get an uplift rate that matched that GPS or got anywhere close. And actually we needed about 4 times the amount of ice mass loss to get anywhere near that GPS recorded uplift. So we deduced that this must be a viscoelastic response, and running a viscoelastic model, we were able to test different Earth properties and constrain the upper mantle here to be 1 times 10 to the 18 or around that value. So there are lots of regional studies like this that have used GPS time series and recent ice mass changes to deduce the upper mantle viscosity. So there's been a subsequent one in the Northern Peninsula, and in Marguerite Bay there's been ice loss since 2002, and also notably in the Amundsen Sea sector, Barletta et al. In 2018 constrained the upper mantle viscosity there to be around 4 times 10 to the 18. And there's also another study looking at slightly longer decadal timescale ice loading changes. So we can use these sort of regional studies and compare the values that have been derived with data sets such as the ANT20 seismic velocity model. So this shows relative variations in Earth structure across Antarctica. And we can compare the values derived by these studies to those derived from data sets such as this from seismic velocity models. And thereby we can build up a picture of 3D Earth structure. Okay, so the last example I want to show is some work that I've been doing in the past year, and this is looking at the potential viscoelastic response to surface mass balance variability. So surface mass balance anomalies, you can broadly think of those as kind of large snowfall events. And I used the RACMO data sets of surface mass balance and removed the long-term mean to find out where the large anomalies are. And you can see that time series here for the last sort of 20 years. And this is for one location on the Antarctic Peninsula. And we can see hovering around 0, we can see large positive and negative anomalies. So that's the location just there. In 2014, there was this large negative anomaly, followed quite swiftly in 2016 by a large positive anomaly. And you can see this kind of spatial pattern of distribution along the west of the peninsula there. So we ran this through an elastic model and compared the model predicted time series with the GPS observed time series at these 3 sites in the sort of mid-peninsula there. And we can compute the WRMS, or the misfit, between the model predictions and the GPS time series. And then rerunning that with a viscoelastic model with an upper mantle viscosity of 2 to 3 times 10 to the 18. We do see quite a large difference actually at these sites. And in fact, the misfit reduces at all of these sites. Now, this is significant because surface mass balance variability, the sort of elastic response to that is usually corrected out of GPS before it's used for GIA to constrain GIA models. But this work is really showing that in regions of low viscosity, we need to also consider this viscoelastic signal as well. So just to sum up, GPS observations provide important insights into how the Earth is deforming and can provide a really useful tool to constrain GIA models. This is why we need to keep the networks going as long as possible. Long time series are important and they get more accurate the more data that we have. And also for regions of rapid change, long time series can record these interesting signals. There are challenges in separating the signals that these sites are recording, both geophysical and non-geophysical, but this also provides us with opportunities to understand more about how the Earth is deforming. And I think in regions of rapid change or low viscosity, we should really move towards a more sort of time series approach rather than estimating rates. And that's because the low viscosity means that the Earth is responding really quickly to different events. And I think we can learn a lot more by using a time series approach. Thank you for your time.
Okay, thank you, Grace. You showed very nicely how the viscosity varies with space in Antarctica. With the post-seismic studies, are those getting similar viscosities, or are those getting different viscosity estimates, or are the locations too different to actually make a comparison?
That's a good question. For the Northern Peninsula, this is actually the best fitting model from the subset that we tried. It actually preferred a Berger's model, as you might expect for the post-seismic. And so for the Northern Peninsula, we constrained a steady state of 4 × 10⁸. So yeah, that matches quite well with what we're seeing from these short-term viscoelastic deformation studies.
Okay, thanks. We'll have a couple more questions from the committee, and then I'll turn it over to some questions from the audience. So first, Barbara, and then Torsten.
Yes, thank you for the nice talk. When I also have a question about the viscosity. When you quote numbers of 10⁸ Pascal seconds, and you say this is for the upper mantle, is that the entire upper mantle? Can you distinguish like the asthenosphere versus or the low viscosity zone?
Yeah, that's a really good question. And based on the simplicity of the models are quite often 3-layer. So we set these kinds of values for the whole of the upper mantle, or at least down to around 400 kilometers depth. So yeah, it's hard to add any more layers in to kind of differentiate that. Particularly with some of these short-term loading studies where the actual ice mass change that is occurring is on quite a small spatial scale. So that would only penetrate down to around 250 kilometers kind of depth. So we can only say that those values are representative of that uppermost mantle.
Thank you.
Following up a little bit on that, I thought the different sources of decadal timescale variations were really fascinating. And you mentioned post-seismic, you mentioned recent deglaciation, but then there are also these climatic cycles where you have larger ice pack, larger snow loads and things like that. And I guess to some extent, they're superimposed everywhere, these effects, but I think there may be, or maybe there are places where one feature is more dominant than another. And I was wondering if you could sort of zoom out a little bit and point out where the challenges are in terms of having these signals superimposed and where there are opportunities to use them, right? Are there places where we can use them to say more about recent deglaciation and things like that?
Yeah, I think West Antarctica really gives us that opportunity because of that low viscosity upper mantle. We're going to be able to see that viscoelastic deformation from all that's going on. And I really think that one of the big challenges is untangling these different signals. from the time series. So yeah, I think particularly the Amundsen Sea sector, where we see these huge deformation signals, might help us tease out a little bit more and separate these signals a little bit more. In contrast, in East Antarctica, where we've got quite high viscosity, we can be fairly certain that we're only going to see an elastic response. So we can almost use that to validate the models a little bit, because we can be quite confident that we're only going to see an elastic response to anything that's happened over a sort of decadal timescale. So yeah, that's a bit of an opportunity, I think, really.
Okay, I'll go with a question that is from our online audience. So this comes from Thomas Givens, and he was asking about Iceland, but it's another region of low mantle viscosity. So Grace, you might be able to answer this one. Could you say something about, can we avoid some of this ice history viscosity structure trade-off, or how does it change when we look at these areas of very low viscosity? If we're looking at, like, say, the last 200 years of ice change or the last 20 years of ice change, could you say a bit more about what is the sensitivity to determining or let's say the potential trade-offs between the Earth model and the ice model on these relatively short timescales?
Yeah, that raises a really interesting question of almost what is the memory of the Earth. It would be really interesting to figure out how long we need to go back for these regions. You know, is it 50 years? Is it 200 years? Is it 2,000 years? And that almost would help when we're thinking about our ice loading model, that in regions of low viscosity, actually, it doesn't matter if we're not quite accurate up until about 2,000 years ago, but we need to focus on getting that last 2,000 years right, almost, because the residual signal from anything older than that is going to be close to zero. So yeah, I think it's really important in those regions to focus on sort of decadal to centennial timescales.
Thanks. So here's another question from the online audience. This is from Greta Bellagamba. And she says, sometimes we have data about ground deformation from leveling or other sources that go back farther in time. Could those data be useful? And are there some strategies for how we would address those longer time scale data? So I think any of our speakers could potentially address this one.
I think any data on a longer time scale would be beneficial for integrating into the observations.
Mm-hmm. Any thoughts from the other? Rebecca, yes. Oh, sorry, Rebecca's muted. Is it your end, Rebecca? Not supposed to be muted. So if it's not coming in, could you type the answer and we'll get back to it? They think it might be with the headset. No, if you could just type the answer into the chat, I can read it out, Rebecca. We'll come back to you in a minute. Yeah, Jessica.
Hi, thanks everyone for great talks in this session. I had a question primarily for Grace about infrastructure needs. You showed East Antarctica looks like it's going to have a nice GPS deployment, but that West Antarctica, or the West Antarctica Peninsula, as well as the Amundsen Sea, is going to, that there's a struggle to keep those networks going. And if you could talk more about the long-term outlook and challenges, that would be helpful, because those areas seem really key to the data that is needed.
Yeah, those areas are really key. In terms of infrastructure, I'm by no means an expert, but I mean, most of the hard work has been done. The GPS are installed, they're running, and they're transmitting. A lot of the stations have had equipment upgrades that mean they're kind of going to be running for longer. So really, the hard work is done, and it's just the funding to keep them going in terms of servicing if they need it and data transmission. So yeah, I think this is kind of even more reason to try and keep them on, rather than pull them out and then have to reinstall at a later date.
Thanks.
Okay, thanks. We have Rebecca's answer. I'll read it out from the chat since the audio wasn't working. But she says that in Northern Europe, the leveling data are already combined with the GNSS data. And I believe in most cases in Northern Europe, the signal is pretty linear over timescales of decades. So they can be fairly easily combined. All right, another question for any of the speakers here. This comes from Nicholas Harmon, and he asks, would seafloor geodesy, in particular bottom pressure, help with constraining models in the oceans around the ice sheets? And maybe also if you could say something about what kind of precision and accuracy would we need from seafloor measurements to make them be a powerful constraint of that sea level redistribution and nearly offshore changes.
So maybe I can say something about that. There's two things to think about when it comes to bottom pressure data. One is, to my knowledge, the current distribution of bottom pressure data is pretty sparse. And so you kind of sort of have to determine how you're going to ingest that. Is that going to be mostly indicative of a large wavelength, which could be okay if that's true. But second point is you're going to capture barystatic sea level. So this is something we can interpret with GIA, but also dynamic ocean. And that is usually the point of that data, is to also be able to say something about the physical oceanography. And so if you don't have a model that's able to either sort this out or ingest it jointly, it's difficult to use, but it's of high interest.
Great, thanks. Another question from our online audience from Sarah Stamps. Could Rebecca or another talk a bit more about the importance of compressible versus incompressible GIA models, and where are the differences in the model predictions? What are the differences in the model predictions?
So let's try my headset again.
It's working.
Perfect. Yes, so compressible versus incompressible. First of all, the Poisson ratios that we apply for the lithosphere and mantle parameters. There we have incompressible or incompressible. But it's also in the GIA equations itself that when we use a compressible material, we use all GIA equations, which means that the density change is included that comes from the deformation of the Earth. Yes, so that's why it's more important to use a compressible, or it's more realistic to use a compressible model. And then the horizontal velocities are the most sensitive observation that we have, where we can see the difference mostly. But even in vertical velocities, we have small differences that are above the GNSS uncertainty level. It's visible. And relative sea level data, it's also important because when we look at longer times back, then we can see difference between a compressible and incompressible model. And even in stress changes, we see a difference between them.
So is it really just sort of computational issues that keep all models from being compressible, or is it something else? Is it just computation limitations?
It's computation more intensive. Yes, definitely. And way more than incompressible. And also because the problem is that compressible models are not that stable. We can create some unstable modes. And that's why it's more sensitive to what we really do with a GA model.
Okay, another question from Nicholas Harmon. This is for Grace Neild. Are the low viscosity regions also associated with volcanism? That is there potentially more partial melt in the asthenosphere to lower the viscosity relative to a melt-free mantle? And is there some possibility of volcanic uplift signal in some of these places?
I think that's certainly true for Iceland, which is associated with volcanic activity. It's not predominantly the case in Antarctica. But certainly for the Antarctic Peninsula, it used to be a subduction zone, which it's thought that the subduction zone kind of went underneath the peninsula and it shut down from south to north. So it's thought that within the mantle there could be sort of a higher water content there. And that's one of the reasons for the lower viscosity there. Jeff, you're probably more qualified to say something about Alaska than me.
Yeah, I mean, I think in Alaska, it's not mostly associated with volcanism. So just low viscosity asthenosphere there. Okay, another question for any of the speakers. This is from Shinichiro Karato. How about comparing the GIA from near field and far field to separate the influence of ice load history from mantle rheology? What are the sensitivities, or maybe say what are some of the differences in sensitivity between the near field data and the far field data to different parts of the Earth structure and different elements of the ice load?
So when you're looking at the data that is from the far field, it is in some ways easier to relate to the mantle rheology, and in some ways it's more difficult. It's easier because it's mostly large wavelengths, so you're going to look at what parameters influence low degree harmonics in the solution, and that's going to be a lot more the lower mantle than the rest of the Earth. But it's harder because it depends on the sum of all of the ice sheets together. And so if you mess one of them, then the entire set is going to be unhappy. Whereas when you're looking at something like the data around Fennoscandia, you need to know the volume of the other ice sheets to some extent, especially the Laurentide, but you're going to be very, very sensitive to how you're refining the ice history in Fennoscandia too, right? So you have it's easier, you have fewer parameters to worry about.
Okay, we're almost to the end of our time. Do we have any, I think we've got all the questions. So I'll have a question here from Barbara.
Yes, so I'm not sure that has been asked already, but what about the importance of lateral variations in viscosity? Because we've been talking about the asthenosphere at 10 to the 18th and the regions that are not, cratons, but under the rest of Antarctica, it's probably much higher viscosity. Would that influence things at the scales that you're working at?
I mean, yeah, I think we will have speakers talk about that specifically in the second session, but definitely, yes, we'll have how many? 6 order of magnitude difference between the low viscosity zones and the high viscosity. It's mostly shallow mantle.
Okay, do we have one final question maybe from in the room? All right, I don't see any more questions. I think we've gotten all the questions online. So thank you to the speakers for 3 wonderful talks and a really great Q&A following them. So let's give one more round of applause to all of them. All right, thanks. We now have a break. Let me check exactly how long it is. We have a 25-minute break. We'll be back at the top of the hour with session 2, which will be moderated by Jessica Warren, with talks from Harriet Lau, Shiji Zhang, and Glenn Milne. And be back here at the top of the hour in 25 minutes for more great talks. Thanks.
Good afternoon, everyone, and welcome to the second session of our meeting today on glacial isostatic adjustment. I will be moderating the second session. My name is Jessica Warren. I'm at the University of Delaware and a member of COSEG. The session is going to be led off by Harriet Lau of Brown University, and the title of her talk is Understanding the Role of Interacting Timescales of Deformation.
Can everybody hear me? Okay, I'm going to share screen now. Oh. This looks good. All right. Let me make this panel small. Great. Okay, thank you, COSEG, for inviting me to speak. And also, I hope everyone had a really good break and ready for another round of talks. And so today, I'll be talking about why it's important to understand how Earth deforms differently to ice changes on variables timescales. And what are those timescales, you might ask? Actually, all the timescales you could possibly imagine. And so I'm going to start, here we go, with a graph of, or a plot of what the rate of sea level changes today due to changes in ice that happened thousands of years ago. And so what you're seeing in blue are places where sea level is rising today, and in red where sea level is falling. And again, this has nothing to do with modern sea level change. This is sea level change we're locked into because two ginormous ice sheets, the Laurentide shown here, I don't know if you can see my mouse. I can't see my mouse. But the Laurentide, which covered most of North America, and the Fennoscandian ice sheet. And again, those ice sheets vanished about 7,000 years ago. And yet today we are still seeing the effects of their demise. And so if we kind of look at DC, where we are, many of us are here today, you can see we're facing sea level rise at pretty rapid rates. And this is because basically the mantle has delayed the subsidence of the crust. And so anthropogenically driven climate change today is really an overprint of climate change driven on the thousands of years timescales to the millions of years timescales. And so we can actually see the record of these interacting timescales in paleoclimate records. And so what I'm showing you are variations in oxygen isotopes as measured in marine sediment cores. And basically this gives you an idea of how global ice volume has changed in the past. And so this is that record about 25,000 years ago. The peak is the last ice age. And so that was about 25,000 years ago. And you see it decrease to today. And so 25,000 years ago, as I mentioned, we were covered by the Laurentide ice sheet and the Fennoscandian ice sheet. But if we kind of zoom out and go back in time, that last glacial maximum was preceded by times that were actually kind of like today, the last interglacial, about 120,000 years ago. And if we zoom further back in time, we actually see that climate flipped in and out of ice ages, paced at around 100,000 years for the last million years, and going even further back in time, about 2.5 million years ago. What you see is that when the Northern Hemisphere ice sheets kind of nucleated, ice ages happened at a completely different timescale, 40,000 years ago, 40,000 year timescales, until mysteriously flipping to this 100,000 year timescales. And really, this is just to emphasize that every single time we grow an ice sheet or shrink an ice sheet, no matter how fast or slow we do this, GIA is induced. And so going back to this picture of today, on top of this record, on top of what we're inheriting from the past, we have to understand and disentangle the signatures ongoing today. And so melting today is happening at tens of years, hundreds of years. And if we look at here, this is a picture of the now long gone Larsen B ice shelf, the size of my new home state, Rhode Island. Thankfully, it's not Texas or something like this. Rhode Island is the smallest state in the Union. What we want to understand is how we disentangle all these different signals of deformation to then understand how we move forward into the future. And one way to do this is to actually look at other geophysical phenomena. So, moving ice deforms the earth, but actually other processes also produce deformation. And so on the kind of short time scales on the left of this figure, if an earthquake strikes, seismic waves ripple through the planet. And these seismic waves, as they ripple, they're causing small amounts of deformation within the Earth's interior. And these are kind of at seconds to sub-seconds kind of time scales. If you wait long enough, these waves can interfere and constructively interfere and kind of produce these whole Earth vibrations that you're seeing here, we call normal modes. And these happen on minutes to hours. If we go kind of longer, Grace Neal talked about this in the first session, post-seismic relaxation, how the Earth recovers after an ice sheet, hours to days to even years afterwards, we can use to understand Earth's deformation. And if we keep moving to longer timescales, we hit glacial isostatic adjustment in response to the last ice age. But even further back, we can hit timescales of plate tectonics. So the millions, tens of millions of years, hundreds of millions of years timescales, where actually Earth flows. And so from short timescales to long timescales, what we do know is that at the short timescale, Earth really behaves nearly elastically. But moving towards these long timescales, Earth behaves like a viscous fluid. And so kind of observing all these different processes and combining insights from experimental data, can we build a general model of deformation that accounts for all these timescales of deformation? Because ultimately, if we want to kind of understand how we move forward in terms of ice melt today, we need some level of generality. And so there is an established model that we've talked about already in the first session, and this is what we call the Maxwell model. And the Maxwell model can describe those two end members of deformation. And so this is what the Maxwell model looks like. It's comprised of an elastic spring and a viscous dashpot in series. And so you can imagine if you applied a stress to this contraption, a really fast stress, the elastic spring will deform. And so just imagine the Earth deforming like an elastic solid. This is what geophysicists do to model GIA. If we start slowing that stress down, the viscous dashpot will take up more of that deformation. And the transition between these two end member models can be anything between hundreds to thousands of years within the Earth's mantle. And that really depends on where you are in the mantle, how hot the mantle is. And so this is basically what most GIA modelers use. There is a growing consensus, though, coming from the rock physics community, that actually the Maxwell model, which I just showed you, isn't quite enough to really explain the full spectrum of deformation that the Earth undergoes. And so what rock physicists do is they actually basically crush rocks, deform rocks, and watch what they do. And so typically, you will take a natural sample at times. So this is shown here on my shelf. This is a sample of the San Carlos peridot. And the green crystals you see are really large olivine crystals. And that's basically the major mineral that makes up most of the uppermost mantle. There's a little soccer player, Manchester United soccer player here shown for scale. And so what rock physicists do is they'll take natural samples and put them inside these kinds of contraptions. And I'm sorry, my mouse doesn't work, but I hope that my explanation is enough to show you where I'm going. Some experimentalists actually use synthetic materials where they kind of fabricate rock-like materials. But ultimately, what you do is you take your sample and confine it at high pressures and temperatures to kind of emulate mantle. And you'll apply stresses of different timescales and basically see what happens with how the sample responds. And really what rock physicists want to do is investigate the grain and the subgrain interactions that fundamentally control macroscopic deformation. And so with all this kind of knowledge, you can build a mechanistic model at the grain scale of what drives and what dictates deformation. And so this is one example from a lab. This is the ANU lab. what you see is that short timescales to long timescales, different types of mechanism of deformation are activated. And so at the short timescale in this model, what you get is a process called elastically accommodated sliding. So viscous sliding of these grain boundaries leads to elastic stress concentrations at the corners. And if you move to longer time scales, those stress concentrations cause diffusion away from those corners. And actually, these first two phases basically produce at the macro scale time-dependent deformation, but it's fully recoverable. Now, if you keep moving to longer time scales, you get to that kind of flow I talked about, those mantle convection time scales. And this is basically what we call diffusion creep. But the important thing here is that the deformation characterized is completely permanent. And ultimately, the Maxwell model can't explain these two first processes. And so there is a search to augment this contraption with some sort of transient component in the middle. And there have been many proposed kind of options, but really our picture of these kinds of contraptions that I've shown you only one example from one lab. Really what's happening at this kind of micro scale level, the description is far from complete. And so we really need to do more experiments. These experiments are very hard to do. You're measuring very tiny amounts of strain at frequencies that are very hard to activate. And so there have been proposals. And so the ideal format of what a viscoelastic model or viscoelastic law might look like is if you know the environment that a rock exists in and some of its fundamental properties, what I've called here the state variables. So this could be the temperature, the pressure of the rock is, the grain size, the composition of the rock. If you have a full description, this viscoelastic law or viscoelastic model, you should be able to predict the deformational properties of that rock at any given time scale. And so this is the ultimate goal that many rock physicists work towards. And so what we try to do is use an example on the macro scale and see what these experimental laws can predict. And so we looked at the case of Greenland. This was a study led by Guy Paxman. And what I'm showing you here, firstly, is Greenland and GPS rates of uplift. But on the right figure, what I'm showing you are viscosity estimates of the subsurface of Greenland made from very different types of observations. And so the first on the left is GIA based on data from the Little Ice Age. So that was about 200 years ago. And then the next is from the last glacial maximum, so about 25,000 years ago. And then on the far right, this is from data based on mantle convection. And so this, again, is kind of tens to hundreds of millions of years. And as you can see, they don't really match. There is a sort of multiple orders of magnitude range. But as you've already gathered from this talk, if you order these processes in time scale, you can see some trend, right? And so GIA from Little Ice Age is kind of low. And if you move to the longer time scale of mantle convection, these viscosity estimates increase. And so this is precisely what those experimental results predict. This is exactly what their laws would say. And so we thought we'd try to implement some of their laws to see what they would say about Greenland. And so what we did was we first took constraints from Greenland's subsurface structure based on seismology. And so again, remember, seismology is kind of on the seconds time scale. And this on the left is that seismic tomographic map we used. And so really, variations in seismic wave speed here, VS, basically give you an indication of how material properties vary on short seismic timescales. And with that kind of viscoelastic law from the experiments, we want to predict how that kind of deformational properties of the Earth vary at much longer timescales. And to get to this point, as I showed you in that flow, we have to first retrieve those intrinsic properties of rock that are ultimately independent of time scale, right? So that temperature, the composition. And so if I bring back that kind of flow of what a viscoelastic law does, this is it here again. And so the first step was to use that kind of seismically constrained structure. and actually do the reverse. And so we used a Bayesian method to do this, but ultimately we used those material properties constrained at seismic timescales. And this, in that viscoelastic law, would actually be an output of that law. And we did the inverse process to retrieve those state variables using the same law. And so what we get are the state variables, right? The temperature, the pressure, the estimates of the grain size. And once you have those inputs, you can then use the same law to then predict structure at other timescales. And so to do this self-consistently, and again, this is the goal of what rock physicists try to do, is to get a viscoelastic law able to explain deformation on a kind of the full spectrum of geophysical processes. And so this is that estimate, one output of the kind of model of the Bayesian inversion that we did of those intrinsic properties. And so temperature on the left, as you can see, much of Greenland sits above anomalously cold mantle. So this is about 200 kilometers depth. And as you move towards Iceland, you can see the influence of the Iceland plume heating up the ambient mantle. And this pattern is sort of reflected in our estimates of melt fraction and grain size. And again, all of these have uncertainties. This is just one such posterior model. And so with these intrinsic properties, we can then predict behavior of Greenland, the kind of deformational behavior on a wide time scale. And so these are predictions of the effective viscosity at different timescales using those intrinsic properties. And here these are used with the experimental model of Take and Yamauchi. And so what you see here on the kind of decadal to centennial timescales at the top, on the top row, the satellite era, the Little Ice Age era, you see low viscosities in general. But if you move towards longer timescales, viscosity starts to increase by an order of magnitude. And again, this is exactly what we saw in those data. There are many reasons why we had conflicting estimates of viscosity, but this certainly could play a role. And so this was basically in me trying to say that these timescales are very important in understanding the response of GIA, because ultimately what you're getting is order of magnitudes variation in viscosity, which really dictates the flow of the mantle. But interacting timescales of GIA also interacts with other systems that also have their own timescales. And so this is sort of an aside to basically demonstrate two examples that are kind of adjacent to GIA, but fundamental to ice change. And so there's also the cryosphere and the sea level, and the sea level change that we're going to discuss briefly. But ultimately, ice elevation is completely controlled, well, very much controlled by GIA. And so here I'm showing you a schematic of a growing ice sheet. As precipitation falls, depending on the altitude, that precipitation can land as snow and be packed, and you grow an ice sheet. If you're below this altitude, precipitation falls as rain, and you're in the ablation zone. And so this altitude is kind of known as the ice equilibrium line. And so you can start seeing, if we grow an ice sheet, the weight of the ice sheet causes the crust to subside. It causes GIA until that ice sheet reaches some glacial maximum. Now, if climate changes to a melt phase, the ice sheet will respond much more quickly than the solid Earth. And so what you actually get is a shrinking ice sheet. Now, the problem is viscous stresses in the mantle delay rebound and keeps the ice sheet at low altitudes. And low altitudes basically enhance melt because you are below that equilibrium line. You are in the ablation zone. And there is this delay. And so understanding how much delay happens is extremely important in understanding ice dynamics also. And so this is the situation in North America today. Much of Canada is rebounding still, even though the ice sheet is completely gone. Now, the other related process is that of sea level. If you keep the ice sheet low, and if you keep it low below sea level, and the ice sheet is connected to the ocean, you will get inundating warm ocean waters that actually enhance ice melt quite drastically, and processes like calving can happen, and you erode an ice sheet extremely quickly. Now, this is exacerbated basically if we have delayed rebound from GIA, which is exactly what happens. And so these two processes coincide and coexist with these interacting timescales of GIA. And this marine inundation was actually thought to be quite important in the demise of the Fennoscandian and Laurentide ice sheet, which had marine-based sectors at their kind of peak. And this today is a possible scenario for Western Antarctica because, as we know, it is a marine-based ice sheet. And so I just want to add these two other systems, the cryosphere and sea level, into the story of GIA. But ultimately, just to summarize, we are facing orders of magnitudes of change when we look at a single measurement of GIA anywhere, really. And so really what we have to understand is the many timescales deformation that Earth has inherited today to enable us to disentangle that signal from the additional melt that's happening at much more rapid paces and actually accelerating paces, right? And until we do that, we can't really say what the future holds. And so as a community, I guess the take-home messages from my talk is that, you know, GIA modelers, firstly, we have to understand how rocks deform on multiple timescales. And this can be done in many ways. We can use macroscopic kind of planetary scale observations of how the Earth's deforming. Many of the first talks discuss this and discuss how we can measure and observe this, but we also could combine this with kind of microphysical insights from the laboratory. And together, finally, we have to be able to implement these modeling insights into our models, so we can account for this deformation. And I think that's the end of my talk, so thank you.
Thank you very much, Harriet, for a really great talk. Do we have any questions from the committee? Rengen?
Thanks very much. Very informative, but I have a question about your lab experiment. The scale you showed us, you had the short-term, transient, and then long-term. It seems like it can be helpful in understanding the process, but first, the question is, what's the short-term and long-term in your, what is it that
Good question.
the time
that
is used? And how do you think this is actually representing? I know it's hard to really kind of repeat that experiment, but you're trying to get some insight to it. And how do you think this is sort of carrying out, how much it's affecting the actual happening versus lab experiments?
Right. Good question. So firstly, the first question is, what timescales are these timescales? I've been pretty vague here, but ultimately the timescales can vary, but what you need to understand is a timescale which we call the Maxwell time. And so this is really basically a sort of balance between where we think viscous processes happen and elastic processes happen. And that will scale along these different processes. And so really the kind of elastically accommodated sliding, because it is at the cusp of experimental resolution in terms of frequency, we think it happens on the seismic timescale. This diffusionally assisted sliding, we think actually happens continuously from the seismic all the way to what we call the Maxwell time, where kind of viscous creep starts to enact. And so really we think this is completely continuous between seismic to, depending on where you are in the mantle, to kind of hundreds to thousands of years. And around then, that's where you might expect more Maxwell fluid. And so for problems that we're thinking about, decadal, centennial problems, these two processes very much are activated when you start melting ice sheets at kind of these modern timescale, post-industrial kind of timescales of melts. And we think they might even impact aspects of the deglaciation. So, we know that 25,000 years ago, we had the last glacial maximum. The ice sheets disappeared around 7,000 years ago, but none of that was steady. It was kind of punctuated. And so there were there were phases like meltwater pulse 1A, which was a collapse of many ice sheets that caused 20 meters of sea level rise globally within a maximum of 300 years. So even though we kind of see them as modern day timescales, across the kind of climate record, these faster timescales are acting. Thank you.
I'm actually, I think we should move on to the next talk to stay on track. But the committee has more questions. There are also questions in Slido. If you're in the audience, feel free to add to them because we have time at the end for discussion. Okay, so our next speaker is Shiji Zhang from the University of Colorado in Boulder. And the title of his presentation is GIA Modeling with 3D Mantle and Lithospheric Structures. And it looks like he's already up on the screen, so you can start whenever you're ready.
Can you hear me well?
Yes.
Can you hear me well?
Yeah, we can hear you. Can you hear me?
Oh, sure. Yes. Yeah.
Yeah. Okay, great. Thanks. I'm going to turn off the mic now.
Okay. Yeah. So today I'm going to talk a little bit about the GIA modeling with a 3D mantle and the lithospherical structure. I guess earlier Barbara actually raised this question. I hope I'll actually be able to answer some of questions along those lines. Okay. Of course, I'd like to acknowledge the contribution from my former student, Kai Xuan, and also my current student, Tao, and also fundings from over the years from NSF and NASA. So I thought, let's see, let me get my pointer. Yeah, pointer. Okay. So this is sort of like a quick, short outline for my presentation. I'm going to actually talk a little bit about two of our recent studies on the effect of 3D, 3D effects. And then I'll actually, introduce this new open source GI modeling package that is actually publicly available on GitHub. And towards the end, I'll have one slide, discussing the current challenge from 3D GI modeling point of view. Okay. Then, of course, I really appreciate quite a few really good talks given before me, and they really gave a lot of really good introduction to the kind of topics that I like to touch on. And of course, the 3D mantle viscosity, we know the Earth is a three-dimensional in terms of structure, as we can see from seismic studies. In this case, is for Antarctic, and that really shows at 300 kilometer depth the dramatic difference between East and West Antarctic, right? And then, of course, from this kind of seismic models, people actually like to infer for mantle viscosities, such as this study by Eric Ivins, recently published. Then, of course, you have to have a few assumptions about the mantle deformation mechanisms, I guess the rheological parameters. Then, given the uncertainties, then you actually can have quite some different realizations of 3D mantle viscosities, right, based on different seismic models and the different rheological parameters. There's actually another type of 3D, say, mantle viscosity structure that we think we actually know even probably better, that is really constrained by various other geophysical and geodynamical processes, such as we know the lithospherical structure or lithospherical thickness varies from mid-ocean ridge and to oceans of relatively older age. And we also know the plate boundaries that are weak and they tend to decouple plates from each other, right? So I'll just give a quick overview on, I guess, the previous studies on effects of 3D viscosity on GIA. Okay, this is probably most likely it's an incomplete review, and I'll just quickly run through them. And so first, there's this type of studies on 3D, I would call temperature-dependent viscosities. That is it basically takes, for example, take the seismic structure, then convert into viscosities and look at their effects on the GIA process. And there are studies that actually show that relative, various data that previously cannot be explained, but actually now can be explained by 3D structures, 3D models. So that's always nice, of course. And there are also studies that try to address the question that is to what extent 1D viscosity structure inferred from GIA observations actually reflect the 3D viscosity structure. The answer to this question, which is an important question, really depends on the nature of the 3D viscosity structure. So it's a bit of complicated. Then there are also studies look at how 3D viscosity structures, such as the spherical thickness variations and play margins, how they actually can influence present-day crust motion. That is, keep in mind, this is to explain the GPS observations. Okay, and then there's also this class of studies on 3D stress-dependent viscosity. Such studies try to reconcile relative sea level and the present-day vertical motion data. For example, GPS again using non-Newtonian rheology. Okay, so I guess. Today, I'm actually going to kind of present two new studies that actually really look at how the 3D viscosity structure may really influence the GIA processes. Okay, and the first study that actually really to look at the what I actually call time-dependent viscosity. Okay, if you think the problem is always viscosity is already too complicated. Actually, I'm going to add another variable, which I actually think is very much relevant. Harriet actually already touched on this a little bit. That is, if you actually consider stress-dependent viscosity, then most likely the mantle viscosity is going to be time-dependent. That's because the stress or GI-induced stress is likely time-dependent, right? Because glaciation histories and all that. And so now in this study, we basically show you GI calculation using stress-dependent viscosity, right? So we're going to use ice models. Here's a I6G, right, for full ice cycle, and then we use this VM5A, which actually for those who know this. The VM5A actually, comes together with the I6G ice model, right? And we're actually going to use VM5A as a background viscosity, but we add stress-dependent viscosity for the upper mantle, okay, with exponent of 3.5. So here, this is sort of rheological equation we used here as a composite rheology. And then we use about 100 bar as the transition stress. And we ignore the background tectonic stress, okay? And so now, I've been kind of doing these clicker questions now, kind of couldn't help to actually pose a question here before we start to show you some results. That is, I'll ask this question, when is the GIA-induced stress in the mantle the largest? The first option is when the surface ice load is largest. That is, for example, at the last glacial maximum, 26,000 years ago, right? We have the thickest ice load on the surface. And that's option A, answer A. Answer B would be when the rate of deglaciation or glaciation is the largest. In this case, could be, say, for example, during meltwater pulse 1A, that's about 14,000 years ago, right? I just threw this option C. I wish there were option for answer D. And so anyway, of course, between an A and B, right? And these are actually kind of serious considerations. Now, okay, well, think about that, right? Give you 5 seconds. Anyway, yeah, if you teach a lot of, many times intro physics classes, this sort of clicker questions we like to throw out to students, right? Anyway, I'll show you the answer here, okay? So we did this calculation GI with a stress-dependent viscosity. I'm showing you here, it's actually the ice height at different time, 26,000 years ago, the last glacial maxima. Of course, you see the thickest ice. This is, right, this is actually, in sort of on North America, right? And then with time, the ice, kind of belt, right? The 14,000 years ago, that's actually when the ice melt the rapidest. Okay, right? And I guess this is middle column really shows you the stress in the up mantle. Okay, here's the answer. You see that the stress actually is the largest during the this is in the up mantle, right? During I guess about 14,000 years ago. That's actually when the ice melt the rapidest, right? And this shouldn't be too surprising to you because mantle stress depends on the strain rate. And when you have the surface ice melt the fastest, then that's actually when you're going to have the largest strain rate in the mantle. And so that will give you the largest stress, right? Now, the third column shows you the effective viscosity at different time. And then it shouldn't be surprising, right, to see at this time, 14,000 years ago, the mantle viscosity is significantly reduced by more than 1 order of magnitude, right? And there's nothing here, really the change except that here we have stress-dependent viscosity. So the stress or the GI-induced stress itself, in this case, will give you about the effective 30 viscosity reduction around this time when the deglaciation is rapidest. Okay, and then of course you get it back to present day, and then the stress is I guess the relaxation is so small, strain rate in mantle is so small, then you don't really, the viscosity, kind of goes back to VM5A, the background viscosity. Okay, right? So that's really, so just sort of saying here, if you start to consider stress-dependent viscosity, then you're going to actually see significant viscosity reduction at a certain time. In this case, actually during the I guess the water, the meltwater pulse 1A, about 14,000 years ago. Okay, and this is what really the non-Newtonian rheology will give to you. Okay, if you think about it, the physics, it's actually quite simple. Now so this actually can have quite a significant impact on relative sea level. So I'll just show you. I mentioned to you during around 14,000 years ago, right? That's actually when the viscosity reduction, significant viscosity reduction that occurs. And during that time, if you actually consider non-Newtonian models that are showing you here, this is really for a site, Frosta in Norway, right? And so 2 calculations, the dashed line is non-Newtonian, stress-dependent viscosity calculations. And the solid line is actually for standard Newtonian calculations, right? So now you actually see during around 14,000 years ago, that's when the viscosity reduction is very significant. And that's actually, so that actually will give you a very rapid sea level falls compared to the Newtonian models, right? It turns out, of course, if you go look at the far side, that is the far field, sort of size, and this is now in this case, the Newtonian models and the non-Newtonian models, they give you almost identical results. That is actually the reason it's quite simple. When you actually far away from the ice and ice sheet, right, the far field, and then the GI-induced stress there in the mantle is very small. So that's not going to change the viscosity that much. So then you actually, Newtonian models and non-Newtonian models for the far side actually will give you almost identical results, okay? So now let's look at the data a little bit. So I already showed you, this side. Now I plot the data here, and it turns out that actually, if you look at the actual data, and the sea level falls, much more rapidly than the prediction from the Newtonian model, that is the Dick-Powell TS I6G plus VM5A. And this slope of the sea level curve here actually kind of very similar to what the non-Newtonian model actually predict, right? So that's, and then now if you look at many other sites, whether in, Finlandia or in North America, and you actually see many of the sites, you see this what we call the L-shaped curves. That is, there are certain times the sea level falls very rapidly, then kind of goes to kind of really at a much gentler slope, okay? And we think this is actually maybe indication of the non-Newtonian rheology is working, okay, right? And so it's a really, it's an interesting point, okay? Now I'm going to actually move to, the second problem that, that is to think about the GIA process with weak plate margins and the plate, the spherical thickness variations. I'm going to argue that, this can really modulate plate tectonic process on more like a 10,000 year time scale. And we know that plate tectonics, of course, it's relatively, it's really driven by mantle convection. It occurs on much longer geological time scale. And the question here is that now you have this GIA process, right? The glacial cycles. That is, to what extent, right? The GIA process actually will modulate the plate tectonic process, right? So now I already showed you this is a sort of a three-dimensional structure that we're going to consider in this GIA calculations. And I should mention that previously, others, researchers actually, they also look at this problem, but mostly they want to understand its effect on present day, the crustal motion. I'm actually talking about the horizontal crustal motion. That is to try to explain the GPS kind of observation. Okay, right. And so here actually we're more interested in the question that is over this glacial cycle timescale overall, how this plate thickness variations and the weak plate margins actually would influence let's say the horizontal motion of the GI-induced horizontal motion. Okay, right. And so we use, again, we use the I6G as a forcing, and we use the VM5A, as a sort of background viscosity structure. But we added the spherical thickness variation, weak plate margins, about 100 kilometer wide. We also consider a very thin ionosphere in this case. We actually also consider compressible mantle, and also even consider crust 1.0. So pretty refined model. And we could do this because we actually can compute, very efficiently, very high resolution numerical models. We're talking about here globally, we're using about a 30 kilometer horizontal resolution, about a 10 kilometer vertical resolution, and we're using about a 35 million elements to resolve the plate boundaries and the spherical thicknesses. Okay, I'm going to talk about the code that we used here right later on. And so now let's actually look at these two cases. One actually is a case with a 1D viscosity structure. This is sort of you can say this is more like similar to the standard VM5A, the GI models, right? And then this, I guess, the case here actually to the right is got a 3D viscosity structures. What I showing you here, the color is the divergency of the horizontal motion, okay? And the vectors, of course, is the horizontal motions, right? So first, you see actually the scale is different for the vectors. When you actually introduce weak plate margins, and the spherical thickness variations, and you actually really see the vectors, the horizontal motions, really increase dramatically. Okay, and you also start to see in this case the plate boundaries and the divergency, right? The blue color means actually, it really means that there's a convergency going on. And you look at the GI-induced horizontal motion, it's not surprising because we're actually seeing the North America plate has some kind of sort of clockwise rotation, right? So that actually gives you negative convergency along the North Atlantic spreading centers, right? So now the point here is really the 3D can have a very large effect on the horizontal motion compared to 1D. This is actually for present day, okay, right? This is for present day. Now let's focus on 3D model, but look back in time, okay? So this is 8,000 years ago, and this is 14,000 years ago, right? Now the color again is really the divergency, but now with a different scale. Actually, actually, I think I made a mistake here. Actually, it's a scale. Oh yeah, it's a different scale. Yeah, it's a larger scale. Right from -3 to positive 3 times 10 to minus 8 per year, okay? What actually you see, in say 8,000 years ago in this case, now again, the scale is different for vectors, right? And not just the divergence, also for the velocity vectors. And now the velocity vectors significantly increased, right? And also you start to see a lot of internal deformation. That is, as we can see from the divergence at this time, the Greenland actually has had a lot of deglaciation. So you see a lot of, sort of divergence or deformation surrounded Greenland. And I would also like to point out here, even because Greenland is so close to Iceland, and the deglaciation of the Greenland actually caused the opening of Atlantic, mid-ocean ridge system across the Iceland even here, okay? So then of course, you going back in time, so 14,000 years ago, actually, we're actually using the scale is 20 millimeter or 2 centimeter per year vector scale here, okay, right? There's now in this case, in North America, this is really when you have a very large deglaciation going on in North America continent, right? Then you have a lot of internal deformation, very strong, and the vectors, horizontal motion vector, it's more than 2-3 centimeter per year, right? And then you further going back in time 21,000 years ago, right? And then this is actually about 110,000 years ago, that actually during the glaciation time. And you actually see, a lot of you may consider as a plane motion, that is a plane rotation, right? For example, 110,000 years ago, you see this clearly counterclockwise rotation, right? That actually give you the kind of concentrate, divergency along the mid-ocean ridge systems, okay? And so now what we want to actually do is to kind of further quantify the GI-induced horizontal crust motion in comparison with the tectonic plate motion, right? And so this is actually what we
Sorry,
have.
Shiji, I'm just going to interrupt for a second because we're running fairly long right now. So if you could wrap up in 3 minutes. We also have a lot of great questions coming in, so I want to make sure we have time for that. Thank you.
Okay, I apologize for this. Okay, I think I'm actually getting fairly close to the end. Okay, so now here actually I'm just showing you the ratio of GI-induced plate rotation to the tectonic plate rotation for North America. Okay, 1D models, dash line, 3D models, the solid line for 3D models. So I just want really you to look at about 10,000 years ago, you see this the ratio is up, it's getting to about 25%. So which means that the GI-induced plane motion for North America is really reached to about 25% of the tectonic plane motion. Okay, it's quite significant, right? And now this is showing the angle between these two vectors, rotation vectors for GI-induced the plane motion and the tectonic plane motion. And so the quick point here is that for the last 10,000 years, and then we see this angle between the two vectors is close to 180 or 140 degrees. That means these two motions is actually the kind of GI-induced motion oppose plate tectonic motion. But there are also other times the GI-induced motion enhance the plane motion. That is when this angle between the two vectors is relatively small. Okay, so I guess here I just want to also show you very quickly. That is, if you actually quantify the spreading rate induced by GIA and then ratio that to the tectonic spreading rate for the slow or ultra slow spreading centers, and such as Iceland and Southwest Indian ridge, and you actually see there are times when this ratio reached to almost like 40%. That is, the GI-induced the spreading rate actually can be up to 40% of the tectonic ones. And you also can see they can really swing, time-dependent swing back from positive to negative ones, okay? And this can have significant implications for volcanism history for Iceland, for example. And we also found that there's actually this, after one full glacial cycle, there's actually net or actual seafloor production, which means degassing, including CO2s, after a full glacial cycle, right? And so now I just want to quickly talk a little bit about this code that we've been using. Okay, and just to say this is a finite element code, right? It actually works on three-dimensional temperature, stress-dependent viscosity, and using this long uniform kind of grids, right? And so really provide a very good resolution, right? And then I would say this this code really runs very efficiently on PC clusters and also massively parallel computers, like we did a test over 6,000 cores, and this is this is open source, and there's users guide, example cases, the publicly available at this GitHub. Anyone can go to download, right? And we're actually also planning to run some possibly online user workshops, on Zoom, right? And so I guess now this is this is just the history of what is our capacity of this code. We don't need to talk much about this, right? And rather I just want to really show you this is the kind of test case we did for this is running for like more than 6,000 CPUs and with efficiency close to the 80%. Okay, right? Some benchmark. And so for this, I guess maybe you can just trust me on my words. That is very accurate. Okay, this is all being published, document, right? The second order accuracy. Okay, and this is for single harmonic, the log number calculations for single harmonic at with different resolutions. And then this is actually the benchmark for the I6G, the VM5A. And I actually want to point out again here in this case, for this particular model with very high resolution, right? As I mentioned, about 35 million elements, about 30 kilometer, horizontal resolution. It took about 10 hours. Okay, it's not days or weeks, right? 10 hours. Using about 400 CPUs. Okay, right? I guess really I don't feel like I needed to mention this challenge on this particular case again. That is a problem that is the ice model and this 1D viscosity model, they're all coupled, right? The fit of the data, and then which basically means that anytime you try to introduce a three-dimensional structure that deviates from the 1D viscosity, you're going to actually reduce the fit of the data, okay, right? Unless you revise the ice model. I think this is a big challenge. I'm pretty sure it's already discussed by previous speakers. So I'm pretty sure Glenn probably will talk about this as well. Okay, right? And then of course I always feel like the community benchmark effort is important. I know Rebecca is actually organized this. It is very important. Okay, so I think that's all I have. So this is really just to recap what I have said. I guess I apologize if we actually run a bit over time. Yeah, that's it. Okay, thank you.
Thank you for an excellent talk. We are going to go straight to the next talk without questions at this time. But if you have, if the audience has questions, please keep putting them in Slido, and we will have time at the end for a discussion. So the final talk of this session is going to be given by Glenn Milne of the University of Ottawa, and his title is Ice Model Development, Challenges and Paths Forward. You can start whenever you're ready.
Okie doke. Thank you, Jessica. Just got to find my slide. Okay.
Can you speak up a little bit? It's a little faint,
Yeah,
so it might be for the audience as well. Thank you.
Yeah, is that better?
Yeah, it's a little better. Thank you.
I'm sorry, I'm using the mic on my laptop. My actual microphone died. Okay, let me, can you see my screen and my pointer okay?
Yes, looks great. Thank you.
Okay. So this is a very broad kind of review and look forward about the ice model side of things. And I appreciate that COSEG is very much solid Earth focused, but you can't separate ice and Earth and GIA modeling. They're coupled, as many people have already talked about. So I'm going to focus a little bit on the ice model, and that'll be like the first 10, 12 minutes of the talk. And then I'm going to talk a bit about kind of a wrap up, kind of where we're at and how I see things moving forward, and kind of summarizing some of the stuff that's already been said, but really looking forward. Where's the field going, and what are some of the more interesting initiatives in moving forward? So let me jump right in. Why isn't that moving? I don't seem to be able to change my slides. Okay. So just a quick summary of ice sheets and what they are and what they're sensitive to. They're very complicated physical systems. You basically got your ice sheet and it interacts on its different boundaries. It interacts with the atmosphere and climate, essentially. That's one of the more important interactions. It interacts with the oceans, temperature, and also ice at the grounding line of flotation and things like that. And it also interacts with the solid earth, which is very much the focus of my talk and GIA type studies. Because the elevation on this bottom surface will push the ice sheet higher or lower, which will impact how it interacts with the climate system. So really, our job as a community in terms of solid Earth ice interactions is better constraining this lower boundary and what it's doing and how it makes the ice sheet evolve over time. So that's really where we're coming from in our field. Now, in terms of constraining these ice models, there's different data sets that we can pull from, and Rebecca's already touched on this a little bit. But I just want to separate it out into two classes of data. There's data that tells you directly about where the ice was and when, and that's really from glacial geology and marine geophysics. That's independent of Earth structure, Earth rheology, and that makes it, these are nice data because they're direct constraints. So Jeff asked earlier, can you build a model that's independent of the Earth? Well, we could, but we'd have to focus really on these data sets only. And even then, you still have to model ice sheets, and when you model them, you have to account for that lower boundary. So you can't, it's not possible to basically generate ice models without thinking about the isostatic response, but you could focus on data sets that are less sensitive to that part of the response. And the typical GIA type data sets that have already been discussed, so sea level changes and GPS data and things like that, they're typical GIA data sets. So they're very sensitive to what the Earth is doing, and therefore the rheology. And we also bring in constraints from glaciology because there's a lot of interesting physics going on here, and that's really captured in glaciological models. There's like a parallel research field that we try and interact with, but ultimately is developed by itself. But I think in recent times, our community and their community are starting to work together to couple these models, and I'll get to that in a second. And for the Antarctic and the Greenland ice sheets, we can also get useful information from ice core records because those ice sheets are still around, and the ice core records give us useful information on their history. But so just to kind of follow on from that, there's really two ways we generate these ice sheet models, and they're very different. So on the left, so I just picked this slide because it was handy. It's from a paper from about 10 years ago. But on one side, you actually run full glaciological models that incorporate all the physics, and you get ice evolution through time. This is just a particular time. I think it's the last glacial maximum. It's like 20,000 years ago. And so this method is one way to do it, but it's time consuming because you have to run these glaciological models. They're computationally intensive. And so, you can't, it's difficult to explore the parameter space, but all the physics is in there. An easier way to do it, and you could argue a more direct way to do it, and this is how, for example, the ICE 5, 6, 7G models are made, and largely how Kurt Lambeck makes his models. You essentially take a grid and you just hand tune the ice thickness to fit sea level or GPS data. There's really no glaciology in these models. It's really just fitting the rebound data. That's it. Now, the nice thing about this is very direct, very simple, and you can, you can fit the kind of margin constraints and things like that, but there's really no glaciology in here. So, the pros and cons to each approach, and I'm not saying one is better than the other, but I'm just saying, just to let you guys know, there's been these two parallel approaches that have been used, and sometimes there's kind of halfway houses as well, where a bit of both have been employed. So, so I guess an important point here is that the resulting model will depend on the isostatic response. In this case, because it's really fitting GIA data, which is telling you a lot about the isostatic response. And in this case, because in these glaciological models, the bed response is built into the physics. So you can't make an ice model independently of Earth structure. That's kind of the key point. So, and Lambert already mentioned that answering Jeff's question. Unfortunately, we can't be independent of the solid Earth. So that's how you build up a regional ice sheet model, but obviously we're looking at global models. And the way we do that is we basically take different regional reconstructions, Northern Hemisphere, Southern Hemisphere, and we add them together, run them through our models, and then we try and fit data from places like in equatorial regions like Barbados, Tahiti, blah, blah, blah. And right now, the community is trying to address a problem where if you add together our best estimates of regional models, we get a sea level rise that's 10 or 20 meters less than you see in these data sites. So we don't have enough ice in these models. And this is a big problem that we're trying to figure out, but we don't have an answer to it yet. And if anyone's interested, there's been a couple of papers that have talked about this issue, but we haven't solved it yet. So the models we have are we have what we have. I'm just telling you that they have some big issues. So now I want to focus in a bit more on the Earth-ice model interaction, because, the focus of this meeting is really about Earth models and how we understand the rheology, but the ice models are coupled, or they depend on the Earth models. And as we push the ice models to make them more realistic with lateral structure and time-dependent viscosities, we have to try and make sure the ice models are keeping up, or else they're going to get disconnected in some way. And this has already been mentioned by Shiji and others. Because a lot of the ice models that the community has available to them are based on 1D spherically symmetric Earth models. And that basically means that these ice models are biased, right? Because they're ignoring lateral structure. And just to kind of make that point kind of explicit, this is a model prediction of sea level 10,000 years ago in kind of Eastern Canada and northeastern US. And this is a 3D model output minus a 1D model output for the same radial viscosity structure. So the only difference between these models is the lateral variations in viscosity. And if you look at this scale bar, we're seeing hundreds of meters of gradient in sea level that the 1D models are not capturing, right? So that means, and this is kind of obvious, you're going from cold cratonic regions like Hudson Bay out to coastal areas with much thinner lithosphere and warmer temperatures, lower viscosities. And a 1D model will try and average that structure. But when you average it, then you're going to be biased. So I guess the point I'm making here is if you take a 1D model that ignores this variability and tune your ice model is going to be wrong, and quite significantly wrong. We're getting differences order 100 meters. That's like a 20% error. So your ice thickness is going to be off by 20% at LGM, roughly, just first order. So this is a major issue that the community has to deal with now. We're pushing these more sophisticated Earth models, but we're using ice models that are wrong because they're based on 1D Earth models. And I think that's really a major challenge that we have to address as a community. So the summary is that's a major bottleneck in moving forward with these more sophisticated models. So how do we deal with this issue? Well, I'm just going to highlight 3 ways. And I should point out that the stuff I'm talking about isn't necessarily things I'm doing in my own research. These are community efforts. Some I'm involved in, some I'm not. I'm just highlighting what I see as ways that will probably, lead to very solid and useful results in the next 5 to 10 years. So one way to deal with this is to actually explicitly use the 3D Earth models to tell so if you build an ice sheet model and a 1D Earth model, you have to tell your 1D Earth model what error it's making. So you have to tell it what the structural error is it's making. And Tarasov and colleagues that can actually do that. They can build in this estimate of structural error, and they can then incorporate that when they're estimating these ice sheet histories. So that's one way to do it. And Lev is doing that now, and he's been doing it. So that's very positive. It's not ideal because it doesn't bring in the information from the 3D model to improve the ice model. To do that, you really need a fully coupled ice model, Earth model, and an Earth model with 3D structure, right? And this is a very young field, but it has a lot of promise. And for example, people like Natalia Gomez, Van Kalker et al. Out in the Netherlands, and Albrecht et al. In Potsdam, they're coupling proper glaciological ice sheet models to full 3D GIA models. And so that's kind of state of the art, but that raises issues because these models are very computationally expensive. So you can't explore the parameter space. You can run them and look for very crude sensitivities, but you're limited. So I think the community has to seek ways to make that process more efficient. And there's some ways to do that. I just want to highlight one. This is a 2D model that tries to simulate what a 3D model can do, but it's much more computationally efficient. And also, I think Lambert mentioned this machine learning. There's been a couple of very preliminary studies that are showing that we can apply machine learning to GIA problems. There's still a lot of work to do, but these early studies show a lot of potential, and they could help us explore the parameter space and do that coupling more efficiently if you can emulate the 3D structure, how it impacts the ice history. And the last thing I want to point out is this, there's adjoint methods that are often used in seismology. So I think these have a lot of potential. A recent paper by Crawford et al. So Ophelia Crawford with David Alatar in Cambridge, they basically took this adjoint method and have developed a theory to apply it to GIA problems. And this holds a huge amount of potential moving forward, not just for constraining the ice model, but also for looking at the Earth model 3D structure. And it's a very efficient way to look at the sensitivities of your ice model or to your data to ice history. And I just wanted to show a quick slide on that. So this was provided by Evelyn Powell at Columbia, who's working with Andrew Lloyd and Jackie Osterman. It's work in progress, so it's still ongoing, but basically you take a 3D Earth model. This is an example for Antarctica. And there's a GPS station down here somewhere where my little pointer is. And you can calculate these kernels for that location, for that data point, and it tells you what your time and spatial sensitivity is to the ice history. So for a 3D model, you're getting ice history sensitivity around that point, but you can see that you're really much in the yellows and blues. So beyond about, a lot of that sensitivity is very recent change in the ice sheet. If you take a 1D model, you can see the sensitivity becomes much older. So this is a really powerful technique to tell you at any given data point what your sensitivity is to the ice history in space and time. And I think this has a lot of potential moving forward. You can take these kernels to do inversions for ice thickness changes through time. Okay, so moving forward in terms of addressing this issue and making these ice sheet models compatible with these kind of state-of-the-art 3D Earth models. You can look at it in two ways, the data side and the model side. So data side, I think really, and this is just my personal opinion, but I think the two ice sheets that we need to pin down better are Antarctica, because they're very data sparse, and North America, because it's so large and covers a lot of space, right? We need better control on those ice sheets in terms of margin position and chronology. And in West Antarctica, essentially any low viscosity regions, we need better control on the recent ice history, because that's what the data are more sensitive to, particularly the GPS data. You're not really seeing back far in time. You're seeing a few thousand years in some places, and that's due to the low viscosity. We need better control on recent ice history changes. And the one last thing I wanted to highlight is, we have all the data from Antarctica or from North America or Greenland or wherever, and that's important data. I'm not, we need that data. But you can also learn a lot if you have data further afield. And I want to just highlight a recent study that is in review, and this is from Udita Mukherjee, who was at Tulane University with Tor Tonquist. So they looked at very precise sea level records at 4 locations around the planet. These are the 4 locations. And specifically looked at rate of change of sea level at these different locations. And they compared this to different ice sheet models that are shown here along the x-axis. And they found that your typical ice sheet models, ANU, ICE 5, 6, 7G, they're not giving enough melt. They're not melting fast enough to really capture these rates in the sea level data. And specifically what these data are telling us that we need more melting from North America, that's the red stuff, compared to Antarctica, which is the blue stuff, the blue part of the column. So, and that's like the opposite of what we had 10 or 20 years ago looking at these models. So these data are very important for partitioning, like globally partitioning and telling us where the melt's coming from at any particular period in time. And this only covers like 9,000 to 7,000 years ago, but it tells us that the models we're using are wrong. So not only are they wrong spatially, but they're wrong chronologically as well, and quite significantly. So we need more of this high precision data. So that's just me thinking top of my head in terms of data, what we need to move forward. In terms of modeling, I think there's really 3 things we need to push, and that's continued development, testing, and applications of these coupled ice Earth models with 3D Earth structure, and hopefully eventually non-Maxwell rheologies, because, you know, transient nonlinear flow is going to play a role as well. And we need to continue methods of development to, you know, to improve the efficiency of these coupled models, because they're just too intensive computationally. We need to explore that. So machine learning and other approaches that are a bit more efficient. And this adjoint method, I think, has a lot of potential moving forward as well, because it really targets where your sensitivities are for a given data set. So that's my icy part finished. How much time do I have, Jessica?
You can go about 3 minutes longer.
3 minutes, okay. So I was asked to put in this slide because, you know, we're passing the torch to the younger generation, and there's been training schools offered for over like 2015, 1923, sponsored by these sponsors are on top, thanks to the sponsors. But we'd like to run more of these schools. This is from Stephanie Sherman at OSU. So I'm just like to encourage colleagues that when they put in funding applications, ask for money to support training schools, because they're really they're always oversubscribed and the feedback is super positive. So we just, you know, and a lot of the work I'm talking about here is led by younger scientists. So we really need to push that and get more of these training schools happening. Okay, so the last, I can't see the title. I think this is wrap up, right? So I'm going to go through this quickly because hopefully it'll lead into the discussion, right? I think that's going to be more important, but just to summarize a few things. So as Harriet said, GIA is a beautiful macro rheology experiment on different time scales, right? And I think we can learn from GIA in terms of what the Earth like inside on these time scales. And the models that we're developing now can really start probing that, as Harriet mentioned. It also gives us constraints on ice and sea level evolution that's essential to understand the climate system. And products for end user communities, not just geodesists. I was asked to talk to geodesists, but also the paleoclimate community. They need GIA model predictions to interpret their data. So we're focused on, we're making these models more accurate. You know, we're building in 3D Earth structure. We're looking at time variable viscosity. We're looking at coupling ice to Earth. These are all great things, and they're going to help us move forward and get more accurate models. And the other good thing about that is if we build in the physics, we can actually engage better with other communities like seismologists and the mineral physicists. We can take their constraints like Harriet was talking about, and we can start a discussion, you know, and go back and forth, macro, micro, are we getting the same answers or not? So that's the good side of these more complicated models, but there's always a bad side. And the bad side is greater complexity, more model parameters, longer run times. You can't explore the parameter space, more non-uniqueness, right? GIA has always been plagued by non-uniqueness because you have the ice and the Earth, and there's ways to try and attack that problem. But as you make the models more complex, that problem only blows up. So that's really the issue I think the community has to deal with in the coming decade, non-uniqueness with these more sophisticated models. So I'm going to end with this. So Harriet talked about Greenland, and Greenland hasn't had enough attention, I think, so far. So Harriet talked about the GPS records. It's a beautiful data set, really important to understand what's going on in Greenland. And the data are shown here as the black symbols. So we take what we think is a good GIA model, and we get the open circles. And you can see the fit is terrible. And so we've been trying to understand this. Why is it such a poor fit? You know, obviously we're missing some physics or the model, the data set is something. So we've been exploring that recently. And to try and understand that, one hypothesis, the one Harriet mentioned, is you can explain it if you bring in transient viscosity and say that viscosity on shorter timescales is lower and there's a large post-little ice age signal. So that's one way to explain it, right? There are other hypotheses here you have to test. So these data are corrected for elastic deformation during the GPS time series. That correction is not easy to make, and you assume an elastic response. So that's another aspect that's probably needs to be looked at more carefully, because the rates seem to be coming down as more recent updates to the data are published. And also, and this is recent work, I think Harriet's familiar with this. So Linda Pan at Harvard with Jerry Mitrovica say if you put in finer viscosity structure shallow in the Earth, you can also explain this problem. You don't need transient. It's another, so basically a thin low viscosity zone beneath the lithosphere can also explain this difference. And recent work in my own group is showing that if you add lateral structure, you can also explain these data without transient rheology. I'm not saying one is correct and the others are wrong. I'm saying it's probably a combination of all three. And this is a beautiful illustration of this non-uniqueness. We don't know what the real answer is, but we need to keep working and talking to each other and bringing in other data sets to find out. So I think these are ways forward with that. And I'm going to stop here because this is going to lead into the discussion anyway. But I think these are aspects that I'd like to discuss with the committee and with other colleagues and with anyone who's listening online. So I'm going to stop there. Thank you.
Thank you, Glenn. That was a really nice example to end the talk on. Before we start the general discussion, I actually wanted to ask you to just give a little bit more context about the training school that you mentioned. This committee is interested in the training and education component. And if you could see what the funding model is for that. Is that an ongoing school that is held on a regular basis, and how does that work?
Is Rebecca still here, or is she gone to bed? Rebecca, are you still here? Because Rebecca's actually been
yes, I'm still here. Yeah. If you can hear me, I can shortly say something. So this training school was the first time in 2009 and 2011, 2015, 2019, 2023. We are actually hoping to have one in 2027 and 2031 at least. Funding was usually for the past 3 schools via the PONET NSF program, but also many others stepped in, like IOTG, EGU, IAG, IX, Polar Canada last time. So it was usually many funding agencies contributing to it, which made it possible to really make it a free event for those coming to the meeting. Or to the school, so that we could really find the students that were really good enough to attend or needed also the school. So we had applications of more than 100 people, and we had only 40 seats. Yeah.
Great, thank you. Okay, I know the committee has a lot of questions. I think Thorsten, is indicating he wants to ask something. So do you want to go?
Thanks, Glenn. This is great exploration of some of the interesting connections and trade-offs. And I was wondering if you could expand a little bit more on the ice model side, where you've shown that people have run glaciologically sort of consistent models and compared those with best fit models. Now, if you look at the differences between the two that are considered robust, where you go like, why? Are those differences that may then indeed be due to the Earth structure, where like, this is a region where 3D variations in viscosity matter, or are there a lot of other places where there's a real mismatch between our understanding of the dynamics of these ice models and what the best fit would be?
It's really, Thorsten, it's really different things. I mean, very few groups are doing the coupled modeling. That's really in its infancy. So I don't think there's really enough out there to start saying why they're different. But the 2 examples I show, that just illustrates data sparsity for one thing. So in the middle of Canada, you have no data to constrain the thickness of the ice, or very little. And you could, if you have a different, I showed one glaciological model and one that's more just hand tuning the thickness to fit the GIA data. But bottom line is there really no data in the middle of Canada where you can really estimate that thickness. Or, okay, GPS, there's some GPS stations, but they're very sparse. So it's really a data sparsity issue. It's particularly in Canada because we just don't have enough GPS constraints.
What about the edges, sort of around things, right? Where you might be a little bit more. So the
edges are better constrained because that's where generally you have information on where the ice margin was at different times. You have sea level data, and you have GPS as well. You have multiple data sets, so you can really pin things down better at the margins. It's really when you get into the interior, and Canada's a bit of an end, or North America is a bit of an end member because it is so big and there's very little data in the middle. And actually moving forward, what I'd like to see is a better population of more GPS sites, maybe the use of INSAR. I think Rebecca showed an INSAR example to really start to fill out these space. Okay, it's only a present day snapshot, but at least it's a constraint.
We're going to go to Mong Han next.
Thank you for your talk. So you showed how important is it to consider 3D and 1D and how much improvement we got. So I was wondering how about that with depth?
Oh, you mean viscosity with depth? Well, I mean, the results I showed these were full global models. So you could take in a different global model based on a different seismic model, and you see slight differences, and sometimes not so slight differences. It depends where you're looking. But, you know, I mean, every ice sheet is a difference. You have North America that's huge, that's sensitive way down into the shallow part of the lower mantle. And then you've got, say, the Greenland ice sheet that really only sees the upper mantle. And then you've got the British ice sheet, which probably only sees the upper mantle. So depending on the ice sheet and the area you're talking about, you know, the depth information is more or less important. But 3D, yeah, it's hard to say. And that's where I think these adjoint kernels are going to be super useful, because at any given observation point, they'll tell us what your sensitivity is to structure at different depths. And that's going to be really neat. And I really think that's going to be a game changer. I'm not involved in that research. I'm plugging it for other colleagues, but I mean, I'd love to be, but that's really going to change the field significantly.
Thank you.
I think Harriet,
We're going to go to Jeff next.
Oh.
Yeah, I have a question for Harriet. So in your model, you had obviously both spatial and temporal, or timescale variations, I should say, in effective viscosity. And the question is the magnitude of the time variations in effective viscosity in a place like Iceland that is overall low viscosity, does that also see orders of magnitude change when we look at, like you saw for Greenland in your case, or would it be larger or smaller in a place where the viscosity is overall lower?
Oh, good question. So if these experimental laws are right, I think in hotter places, the difference is muted. But also you're shifting the Maxwell time to, you know, faster timescales. So those processes are happening even faster than you think. And so there's a bit of a temperature dependence on the transient as well. Again, if these experimental models are correct. Yeah.
So for example, for Iceland, what kind of range over, I guess, well, something that, you know, on let's say tens of thousands of years, it fully relaxes anyway, I guess, regardless. But yeah, what sort of a timescale difference might we see in a place like Iceland if we're looking at a really short timescale process versus let's say 1,000-year timescale process?
I'm actually not sure. Maybe mainly because on thousands of years time scale, it probably would relax quicker because it's low viscosity. So you might not be able to disentangle those signatures, at least observationally. Theoretically, we could say there are probably differences. Whether we'd be able to see them is another question. So I actually, off the top of my head, don't know. But Iceland is an interesting case, and you know, obviously there are ice caps that are melting at different rates, but it's also undergoing other processes, like the tides, ocean tides in Iceland are massive, and so you can sort of get forcings that can give you indications of non-elastic rheology at the kind of hourly time scale. So it's an interesting, rich area, but also very complicated area because there's a lot of melt. There's, you know, all these things that start throwing you off. But yeah, I hope that kind of gave you a bit of at least some intuition on it. I had a question for Glenn. Is that okay? Or at least like a little follow-up to what you were discussing.
You have the microphone.
I do have them. I won't turn it off. I'll just keep it on and hog this just briefly. But it was interesting when Torsten asked you about constraining the ice model in other ways. And I've just come across some really recently interesting papers that, again, it's just not in my field, so I don't really know. But there are, you know, you can sort of explore the drainage patterns, right, through time. And so if there's a sort of flux into the Gulf of Mexico, that sort of indicates a retreat of the Laurentide. And, you know, if the fluxes are into the Arctic Ocean, maybe that's an advance. And so are these sorts of constraints, these kind of more geochemical constraints,
Could these be
that's a
worked
good point.
in?
Some ice models, and I know Lev Tarasov, he has basically a hydrology component in his
Right.
glaciological model, and he can predict these signals, and therefore he can use these data. And they don't all do it, but I think it's information that can be used if you have it built into your model, and it can be very powerful. Yeah.
I actually had a question for Harriet about the model, the rheology model that's in there, which is based on diffusion mechanisms. And I think a lot of that drives from work on attenuation, in fact. And in the last 5 years or so, there's been a lot of work on dislocation mechanisms and things like low temperature plasticity, which is really another way that you can, in some of the recent dislocation models, get at transient creep. And I'm wondering if you've looked at implicating any of those newer models into this.
Yeah, very interesting, a lot of interesting work going on. I've been talking to kind of Lars Hansen about these sorts of mechanisms, for example, these LTP, low temperature plasticity. Yeah, I mean, I currently don't. They do add an element of complexity. And I think these models are currently in their somewhat infancy in terms of being able to I mean, they've been applied in a few cases, I understand, but not in GIA so much, right? But they would be very interesting, and you certainly reach the stress levels that would activate these processes. It's interesting because so much of the rock physics community, as a lot of those papers, firstly, as someone not in that community, I find the literature, I need to really read it about 70 times before I really understand what's going on. And I still don't, because I haven't read it 70 times. But then also, you know, a lot, you mentioned attenuation, a lot of those experiments were geared towards seismology to explain the attenuation of waves and how dispersion happens in terms of how do you move from a seismic tomography model and actually interpreting that model in terms of the physics, underlying physics. And I think that's the bridge, right? We have a VS model, a pretty picture, but what does that mean? And so because those experiments were sort of performed to the audience of attenuation, to the audience of seismologists, it's hard to be picked up. We don't talk about attenuation, even though that's ultimately what's happening. We talk about viscosity, we talk about viscous dash parts. So the language, there's a little bit of a disconnect. And I think Glenn said it at the end, is to be able to talk to these different communities. I think that would really help. So yeah, dislocation for sure at some point.
Great. Yeah, I mean, I think also sometimes there's a feeling that in the rock deformation community that the diffusional mechanisms can be easier to implement in the attenuation experiments. I think that's really the only regime that they could access for those measurements. But that the dislocation mechanisms, that dislocation-driven mechanisms seem to be what dominates a lot of rheology, but they are, I understand that they introduce a lot of complexity in the models, that they're very nonlinear. And yes, that it, you guys have done a nice job in this session of showing how much the computational power requirements increase when you add in all these complexities. We have I'm going to do a question next for Shiji out of the chat. This is from Aidan Janney, who said, thanks for a great talk. And then how much does the plate motion depend on upper mantle versus lower mantle viscosity? And does the dependence change based on the time scale? Do you want me to read it again?
I think sure. Let's see. I understand the question. It feels like the plane motion is controlled by anything touched with a plane. So up mantle viscosity is probably more important than the lower mantle, I would say. And also plate boundaries. That's why plate boundaries is so important as well. And so anything kind of touch down the plate itself, right? Viscosity wise, yeah.
Great, thanks. And then we are going to do another question from the chat. So a question for Harriet from Max Bezeta. What seismic observables were used to estimate temperature, melt fraction, and grain size beneath Greenland, and how did you handle trade-offs? And I think Glenn should also feel free to jump in when he wants.
Yeah, so we used a seismic tomography model that constrain shear wave velocity. And so that would give you basically the shear modulus at seismic timescales. So I think that was given to us at 1 Hertz. There was a attached attenuation model. And while it wasn't a 3D attenuation model, it was a 1D attenuation model. We sort of implemented that into the workflow, even though ideally we'd have a frequency dependent Q model as well, and it would be 3D. But obviously that's very hard to constrain seismically. Q is very difficult to measure. And so that's what we use to constrain our model. There were trade-offs for sure. And, you know, I think if you have 3D Q and 3D VS, that really helps with narrowing down the trade-offs in terms of things like melt and stuff. And so if you, in that study, there are kind of large posterior kind of distributions which reflect the trade-offs and the covariances. And so you can do something like, you know, decrease the grain size, and that might have the same measure as increasing the temperature on VS. And so there are plenty of trade-offs. And it's interesting, the trade-offs in the intrinsic properties don't always kind of filter out into very different macroscopic mechanical properties. I'm not sure if I sort of I'm not explaining that well, but you can have like massive variations and trade-offs in temperature, grain size, melt. But the viscosity that comes out of that could seem a little bit less like of a mess, basically. And so kind of those different processes can actually produce mechanically similar behavior.
If I can just add quickly to that, that also means that from point of view of the observations, we can't distinguish between them because they produce the same deformation. So for us, when you give us a map of viscosity, whether it comes from an estimate, a different estimate of grain size or different estimate of temperature, it all's added to the same map. We can't tell you which one is correct because they produce the exact same GIA.
Torsten?
Yeah, just to quickly follow up on that, of course, this then sort of reminds us of the other constraints that we have where, say, grain size and temperature have a different effect on the density. And so if you look at things like dynamic topography, you could be able to tell those apart. And there's the sort of general mantle circulation aspect of things that will affect things like the background stress, for example. And Shiji mentioned that in his tests, he used a very low background stress, and so that makes nonlinear rheologies more important. If the background stress is higher, then the effect of the ice is just not large enough. And those background stresses will in turn depend on the 3D viscosity variations in ways that complicate things, but they're also accessible through modeling, leading to interesting local variations in the nonlinearity, for instance, in light of where the cratons are.
And I think to add on this, Grace touched on this at the end of her talk. You know, we did say that Lambert and I said, yeah, it is really hard to, pick out what underlying physical intrinsic property could give rise to this single rate of GPS uplift. But, you know, Grace did kind of emphasize getting full time series is very important. And, you know, I kind of flippantly said temperature and grain size have these trade-offs, but in frequency, they look very different. If you think about that time scale effect on viscosity, it looks very different. And so, you know, there are ways if we keep GPS observations alive in Antarctica, that would help.
Barbara?
Brings me, I've been wanting to ask this question. I mean, you've been talking, several of you have been talking about using machine learning to help accelerate the, parameter space, study. But I'm wondering, are these processes linear enough that machine learning can really help you with this? Or that you will really, get the right answers? Because we've been talking about all these complexities and things feeding back into each other.
I can start and others can jump in. It's a great question because there's only been 2 papers so far, and those have indicated, I mean, so for example, the work we've been doing, we've been trying to emulate the difference between a 3D and a 1D model. So since we're focusing on the differences, we lose some of that nonlinearity, and it makes it more tractable. And I think the results, they're not. But the problem we looked at, it gave us, we could simulate the full 3D model relatively well. So essentially what you do is you emulate the difference, and then you add your difference to just a simple 1D model output. And you can basically, I can't remember the details, but you're usually within 90%. Your error is not more than 10%. For looking at sea level data, for example. So the potential's there, but it does need to be explored a lot more, and particularly in terms of putting in different ice histories and things like that, because that will then complicate things more. But the potential's there, and it's one way to tackle that problem. And I think it needs, I think it should be explored a bit further.
Yeah, and if I can just follow up on that, I would distinguish here different types of machine learning you can do. Glenn was talking about the adjoint method being a very powerful and efficient method, and I think that's very true. My current understanding of that is that it involves a certain linearization of the error structure, because you're going to look at the gradient around a certain part of your parameter space. Whereas you can also think about on the emulator, if the training of the model gets good enough that you have very high fidelity of your emulator, then you can think about doing MCMC, which is a different approach. And then I don't think that you would lose the nonlinearity if you did that. Obviously, there's other reasons to compromise the type of parameter search. If you have to invert 3D with all of the parameter space, it's still not feasible to do MCMC, even if you're really fast, because there's way too much dimensionality. So we need to be aware of the trade-off between these different methods and be mindful of what we can simplify and not. And I think as of now, it still comes in by trial and error.
Shiji, do you want to go next?
Sure. Yeah, I like to kind of make some comments here. And the way I see it is this problem is complicated. And also in terms of the GIS studies, I would say maybe 95% or maybe 99% of the studies are actually based on 1D models. So the complexity, I actually think the system is really complicated. And I don't think we actually fully understand the complexity yet. I mean, I read talk about the complexity from physics point of view, right? And that's all well taken. It's very important. I guess just from the modeling point of view, you look at the treated Earth as a viscoelastic, whatever system you call that, and then you apply the ice load, right? And then you kind of ask what kind of response the Earth would have. And for three-dimensional Earth, we don't really know. That's my point of view. And I think it's Barbara asked a question about the nonlinearity. I mean, I think it's a very important question. We don't really fully understand. I would say that maybe, a lot of more, say, numerical modeling that is needed, right, to really understand how the system reacts. I mean, Thorsten mentioned about how tectonic background stress interact with the sort of much short-term stress loading, right? I don't think that actually physically that problem is formulated, very clearly, right? Because it's not you simply do like add a stress term to this system, because we're talking about let's say if you think about it's a really high frequency loading, right, versus a very gentle long-term tectonic stress loading. How the two systems interact with each other, I don't really know if we actually really understand the system like that. So, I mean, I guess to do the calculation is trivial relatively. Again, we can add that tectonic background stress, whatever, 10 bar or 10 bar or 100 bar and there, and you can expect the results, but physically exactly how the system operates, I think it's still needs a lot of explorations. So I guess that's kind of my take on some of the discussions. It's just really, I think from the numerical point of view, or the full considering the full scale physics, and there's just a lot of unknowns we don't out there. Yeah, so.
Okay, so we're going to go to Glenn for a quick comment. And I don't know also if Barbara wanted to say anything as well, but otherwise Glenn is going to have a comment and then we will go to Steve Niram for our wrap up.
Yeah, I just want to go back to, so Grace talked about this, looking at full time series. And I just want to make the point that, if we're looking to tease out different time variable rheological responses like non-Newtonian flow versus transient, the only way, these could be quite subtle signals in, say, GPS records. The only way to really tease them out accurately is to have a nice thickness history at the same location covering the same period. You have got to pull the ice model out of it if you want to really find out what the Earth is doing. And that's why you need these long time series. And I think it's absolutely crazy that some of these stations are being dismantled. I mean, 10, 20, 30 years is what we need to really start seeing these signals with complementary ICESat data looking at ice sheet thickness. And this is like a golden era that we're kind of just going to ignore if we start losing these GPS stations. It just doesn't make any sense.
That is an excellent point to end on. Thank you to all of the panelists for your contributions, and we'll do a round of applause and then we're going to go to Steve for wrap up.
All right, well, this has been a great series of talks. I know I personally have learned a lot today, and I'll try to summarize all these talks, which is challenging to say the least, because we covered a lot of territory here. So Rebecca Steffen got us started with an overview of GIA models and observations. She discussed the various outputs of GIA models and related them to different types of observations. And she also discussed glacially induced stresses and seismicity and their importance to GIA science. And then we had Lambert Caron talk to us about the importance of GIA for modeling satellite gravity measurements. Talked about GRACE and GRACE follow-on and what that data tells us. Discussed how GIA limits the accuracy of ice sheet mass loss estimates, and also the interpretation of North American water storage signals. He discussed the challenges of how to weight different observational data sets, GNSS, GRACE, sea level records, et cetera, and discussed the need for standardization within the GIA community around some of these modeling and data issues. He also commented at the end that we face challenges in characterizing the errors in GIA models that stem from both mantle rheology and ice history. And then we had Grace Neal talk about a discussion of using GNSS data to constrain GIA models, and she focused on Antarctica. She discussed the challenges of untangling deformation signals in a variety of observations, but most importantly, GNSS data, specifically the long-term deformation signals from the last deglaciation versus the short-term changes from present-day ice mass changes due to GIA. She showed estimates of mantle viscosity estimates across Antarctica and how that affects these GIA models in Antarctica. And finally, she emphasized the need to keep GNSS networks in Antarctica and elsewhere going, because long time series are needed to characterize the GIA response. And then we had Harriet Lau talk about disentangling different timescales of deformation, a common theme in the talks today. She talked about how the Earth behaves elastically at shorter timescales, but viscoelastically at longer timescales, and further talked about how that aspect of it might impact future ice sheet mass loss. Then she also talked about the connection of all this to rock physics and the how we're estimating viscoelastic models from rock samples. She showed an improved viscoelastic model from Greenland related to these ideas. And ended up with a comment about how the importance of understanding how rocks deform on multiple timescales. And then we had Shiji Zhang talk about the challenges of understanding observations of processes on different timescales, and also how we interpret those observations with uneven spatial and temporal distribution, and untangling all that from ice sheet model layers. He also talked about the time-dependent viscosity due to stress dependence, which depends on the ice load as well as the rate of ice sheet mass loss. And he also discussed how GIA can modulate plate tectonic processes. And Shiji finished up with discussion of new open source code for modeling GIA that includes the effects of 3D mantle and mesospheric structure. And then finally, Glenn Milne wrapped up the day for us by discussing paths for the development of better ice loading models, showed how there's still ice missing in the models when compared to sea level records, discussed how ice models are wrong sometimes because they've depended on a 1D Earth model and they need to move to 3D models and be coupled together. He discussed the need for more longer term sea level records. He also commented that paths forward might include using adjoint methods and machine learning methods. And ultimately, Glenn commented that GIA studies not only provide constraints on Earth rheology, which is what we talked a lot about today, but also provide insights into future changes in land ice and the evolution of sea level. So that's kind of a little summary of what we discussed today. I want to thank the speakers. They put a lot of effort in these talks, and it showed. I'd also like to thank everybody that joined online. Hope you all got something out of our workshop today. And with that, we'll conclude. Thank you.